Okay, good morning. Let's start with the new week, new day, and new lecture. This time it will be on non-destructive characterization of radioactive waste. On Friday, we talked about the destructive characterization. So let's take a look on other methods for non-destructive characterization of radioactive waste. Just for general information again, that today we know approximately 3,000 different nuclides, among them only 266 stable, and other nuclides, they're radioactive, so they're radionuclides. And as far as most of the decays, alpha, beta, beta plus, beta minus, or electron capture, as far as all these types of, most of them are accompanied with the gamma radiation. That means that we can use it to detect a lot of different radionuclides. I put here this classification of radionuclides by half-life, because very often, and it will be later in this lecture, very often we can find some exotic radionuclides in our gamma spectrum, but we should look really on the half-life of this nuclide. If we found the radionuclide with the half-life, I don't know, 1 millisecond, that means that's probably something wrong with our spectrum or with our identification. So we'll see it a bit later. So why we may perform this non-destructive characterization? It is for several aims. Either it's just visualization of the contact, what is inside the drum. For this, we can use something like X-ray tomography, conventional industrial X-ray tomography. Or we would like to find or analyze the distribution of the radiation sources in the package. Or this first and the third one, they are very close to each other, to determine the physical properties of the of our radioactive waste of our package, because it is important sometimes to see if there is water inside the canister or some other problems maybe that are not reliable for the final repository or for the storage of the radioactive waste. And of course, it is determination of the key radionuclides. We should characterize the content of the radionuclides to be sure that the class of our radioactive waste is the same as we documented previously. And these methods can be divided on two parts. Either it is non-destructive assay. In this, with these methods, we analyze the radionuclide composition of the radioactive waste or of our package, and non-destructive examination. And examination means that we analyze physical and mechanical and maybe chemical properties of our material inside the package. And for radionuclide composition, we can use either gamma methods or neutron methods. So we can divide these two methods, object and neutron methods, as passive. So using the irradiation of the gamma quanta from the object itself, or so-called active methods. So we irradiate our package with neutrons, for example, and we analyze what is happening inside the drums, what kind of gamma particles are emitted as a result of this irradiation. So due to the fact that gamma radiation goes from the nucleus, when the energy of the excited nucleus go from one level to another, That means that the energy of gamma quanta is very specific. So gamma quanta have some certain energy, and this energy is really specific for certain radionuclide. So we can use this discrete structure of the spectrum of the gamma quanta to identify the radionuclides, because the specific energy related to the certain radionuclide. And gamma radiation, so from one point of view, it is not very good because we should shield ourselves from the gamma radiation. But from another point of view, the high penetration ability of gamma radiation is good because it can go out of the sample and we can analyze it. Yeah, we can detect it and analyze. And as I mentioned already, the most of the decays, they are accompanied with the gamma radiation, so we can use it easily. So there is a general scheme or block scheme of the any gamma spectrometer. So there is only one detail that is specific for high purity germanium detectors. It is the vessel with the liquid nitrogen, or it can be another cooling system based on the Peltier elements. Anyway, it is system to cool down the detector. We have electronic system that provide the high voltage for the detector. And there is analog to digital converter system. So together it is multi-channel analyzer. So the multi-channel analyzer distribute all the signals that are coming from this ADC. It divided all the signals by the different channels depending on the value of these pulses from the detector. And then we analyze this spectrum, so this distribution of the events in every channel. Let's say it is spectrum. We analyze it with some software, depending on what you have, either Maestro, LCRM, or some other softwares that you use. So this multi-channel analyzer, again, it's very important, but because from the height of the pulse, we can analyze the energy of the gamma quanta. So the detector itself doesn't give us information about the energy of gamma quanta. It doesn't know about the energy of gamma quanta. All the detector knows is just this pulse that is a result of the interaction of gamma quanta with our system, with our detection system. But then, based on this height of the pulse, we distribute all these pulses to different channels. Depending on your system, it can be 1,000, 2,000, and up to 16,000 channels. The more channels, the better energy resolution, if you have appropriate system again. And your system just distribute all these pulses, all these signals by these channels. And then we calibrate our system with the standard sources. And from these standard sources, we know that, for example, channel number 57 is equal to the energy of 20 kiloelectron volts. And we have this calibration curve, number of channel and the energy of gamma quanta. And we put this calibration to our system. And when we see the spectrum, we don't see channels anymore. We see just the value of the energies of the gamma quanta. But it's just the recalculation of this number of channels to the energy. Yeah. Again, detectors doesn't know about energy and nothing. Yeah. So again, how the spectrum is constructed, or what we can see on the spectrum of the gamma quantum. Again, as we discussed previously, first of all, we identify our radionuclide by the peak of the total absorption, total energy absorption, and it is result either of the photoelectric effect, or it is sum of all the effects that are going on inside our detector. So it's Compton scattering and the photoelectric effect of the scattered gamma quanta, etc. So all these events, they're so fast that they look like only one event for our detector. So it looks like one single of the total absorption of energy, and we use exactly this peak for identification of our radionuclide. But there is possible processes of losing the energy due to the Compton scattering, and thus we observe this continuum, this even distribution of the scattered energy that we called Compton continuum. So next, if we have gamma quanta with the energies higher than 1022 kiloelectron volts, that means that another mechanisms of interaction, the production of electron and positron pairs, can occur. And if due to the annihilation of the positron, all this production of two gamma quanta with the energies of 511 kiloelectron volts, if these two gamma quanta they are absorbed in the detector, in the material of the detector, that means that we don't lose any energy, and we observe again the peak of the total energy absorption. But in some cases, one of the gamma quanta can escape from the from the detector and not be detected, this gamma quanta. So we lose the energy of 511 kiloelectron volts. And if it is only one gamma quantum, it is single escape peak, and thus we observed a peak with the energy less than the total energy absorption. So it's minus 511 kiloelectron volts. Or if both of these gamma quanta escaped, so it is a double escape peak, and we observe the third peak with the energy less than our main peak by the 1022 kiloelectron volts. But the annihilation, it is a process that requires some time. So if you remember, on Friday we discussed that it requires some time for positron to stop, and only when it stops, then it can interact with the electron and annihilate. So this stopping of the positron takes some time. And this time can be enough for the detector to detect this event as a separate event. And thus, this annihilation of the positron, we will observe as the separated peak. And we will observe this peak of annihilation with this energy of 511 kiloelectron volts. So it is another peak. Also, as far as very often we measure our samples inside the lead shielding, the interaction of gamma quantum with lead leads to the formation of the characteristic X-ray of the lead. And thus, we can observe, we can detect by our detection system the X-ray. So it is the secondary process in the shielding material. So this X-ray comes out from the shielding materials as a result of interaction of gamma quantum with these shielding materials. And thus we observe another peak. So there are several peaks of the characteristic X-ray radiation from lead. It's 74, 75, and 88 kiloelectron volts. So we observe this. I put here only one peak. Also, due to the Compton scattering of the gamma radiation, inside the shielding material, we can observe the peak of the this backscattered gamma quantum. And it has a certain energy, because we can calculate this momentum of the energy of the gamma quanta that goes on the backward direction from the shielding material, and we will observe this peak, this backscattered gamma quanta. So also, if we have this scheme of the excited states of our daughter nuclide, there can be several gamma lines, separated gamma lines that goes one after another. And we will observe these two separated gamma lines, so it's good. But also, if these events are too fast or the activity is very high, for our detection system, these two peaks cannot be separated due to the time resolution, maybe bad time resolution or very high activity of the sample. And we will observe the peak that is actually the sum of these two peaks, because the total energy will be just the sum of these two peaks. So in total, with only one peak, our general peak, actually we can observe more 5 or 6 peaks in our gamma spectrum only from one radionuclide. Yeah, okay. So interpretation of the gamma spectrum can be very difficult if you don't know about all these processes. Fortunately, modern softwares, they can take into account all these processes, but anyway, only operator is responsible for the correct interpretation of the spectrum. Yeah? So even if your software gives you this list of the radionuclides, you always should take a look on the half-lives, on the interpretation of the gamma lines. Okay, next problem or let's say feature of the detection of gamma radiation from the big sample, from the drum with the radioactive waste. It is the absorption of the gamma radiation in the walls and in the sample itself. So if we have gamma radiation that goes from our container, there is an absorption either in the walls of the container or in the material itself. So actually, we will detect less gamma radiation that it actually present in our sample due to the absorption in the material. And to take into account all this absorption phenomenon, we should calibrate and identify the efficiency of this absorption by different materials. So actually, it is not only one material, it's combination of different materials. So it's a sample itself. It is some steel, so steel walls of the container. It can be lead shielding, and also our detector itself is covered with aluminum and some other materials. So there are a lot of different materials that are laying between our radionuclide and our detection system. And we can take all of this material into account if we calculate or determine the attenuation coefficient that we can use to calculate this efficiency of the absorption. Another value that sometimes is used, it is the transmittance value that is equal to this exponent, where mu is the attenuation coefficient for our material. This Greek letter rho is density, x is the thickness of our sample. And actually, we can either determine it experimentally, this attenuation coefficient, or we can calculate if we can calculate all these cross sections of photoelectric effect, Compton scattering, electron pair production. We can calculate it from the specific equations, and we can just summarize all of this cross section to calculate our attenuation coefficient. And then there is a simple law for point source of gamma radiation. This attenuation can be calculated easily with this exponential law. And the mass attenuation coefficient can be calculated from the tables. So it's already a lot of databases that can be used for calculation of this attenuation coefficient. Even if you have a complex mixture of different elements, so it really depends on the elemental composition of your material. If you know the fraction of your element, you simply calculate this sum of the attenuation of your element number I multiplied by the fraction of this element in your material, and you just calculate this total mass attenuation for certain energy of the gamma quant, because it depends on the energy of gamma quant. Sometimes we use the value that is, let's say, sometimes can be more convenient to use. So it's a reciprocal of the attenuation coefficient that is called free path length of the interaction of the ionizing radiation with matter. And physical explanation maybe not very correct, but just to understand what does it mean. So this free path, it is the mean distance of the ionizing radiation that takes for ionizing radiation to interact with matter. So if this free path length is 1 micrometer, that means that after 1 micrometer, ionizing radiation interacts with matter, but before this 1 micrometer, it doesn't interact. So, and this, it is not liters, it is this value, free pathway. If the thickness of your material is 1 free pathway, so it's 37% of interaction of ionizing radiation with your matter. So only 37%, sorry, will pass through this thickness of the material if it is 1L. If it is 5L, you can simply put it here. Yeah, it will be exponent in -5. So it will be only 0.7% of the all ionizing interaction, ionizing radiation that goes through the material. And if it is 7L, so it's less than 0.1%. So the self-absorption of the material depends on the material or the elemental composition of the material, as we can see from here. It depends, of course, on the volume. So that means the thickness, yeah, of the material and the shape. And of course, it depends, this efficiency of detection depends on the orientation of your detection system and your sample. With this parameter, free pathway, we can say that there is infinite thickness of the layer of matter. That means that all the ionizing radiation is absorbed in this material. And as far as for 7L thickness, it on less than 0.1% is going through this thickness. Usually we take as this infinite thickness this number 7L for the material. That means that sometimes for heavy materials, like for lead, for example, sometimes this infinite thickness may be less than 1 millimeter. And if you have a drum of 200 liters, and if you have some mixture of the iron and light materials and heavy materials, sometimes you can get this infinite thickness too small that no gamma radiation will go from this drum, only from the very surface layer of this drum. So it should be taken into account. And this is one of the example for americium, for example. The energy of gamma radiation from americium is very low, so it's only 59 kiloelectron volts. And again, if we have this shape of the of our sample, we will measure around 40% of all the gamma radiation that goes from the sample. But if the sample will be too bulky, we will the efficiency of the detection will be less than 1%. So it's very important to calibrate the efficiency of your detection system and of your sample geometry. And to do this, when we are working in the lab, usually we take two geometries. Either it is point source, standard sources. So it's just a small drop of the gamma radiation, gamma radiating radionuclide with the known activity and of course with the known energy of gamma radiation. So we know the energy, we know the activity, and we can calibrate our detector towards the energy, towards the efficiency, total efficiency of the detection. Or if we measure samples with low activity, very often we use so-called Marinelli vessels, and so these vessels, they're just put on the detector, but we can put here volume of the sample up to 1 liter or sometimes even more, maybe 2 liters vessels, but normally 1 liter is enough. And it is absolutely different geometry. Yeah, so we should calibrate our detector towards this geometry. And of course, for detection of the radiation in drums, in barrels, there are specific sources, standard sources of these big bulky materials also. Fortunately, again, today we have softwares that allow us to make the calculation of these efficiency parameters. To do this, different softwares, they use Monte Carlo simulation of the radiation and interaction of this radiation with the material of the detector. Many softwares, they already have some standard detectors, model of the standard detectors inside the database. So the materials of the detectors, the shape of the detectors, but you can build your own model and it will be used for calculation of these efficiency curves. So as the result, you obtain this efficiency curve calculated by the software. So it is efficiency depending on the energy of the gamma radiation. So it's very convenient, but of course you should control these calculations by using these standard sources just to check if the calculation is correct. Yeah, and you can use several points or use, for example, European 152. It's very good radiation source, standard source, because it has several gamma lines, intensive gamma lines, and you can check this calibration curves at different points with one gamma source. But of course, for low energy radiation, you should use this americium 241, for example, as a standard source to check if this very sensitive area is calibrated correctly. Again, let's compare different detectors, different materials of the detectors towards the energy resolution. It's one of the, I think, the most famous example, the most famous picture when we compare the resolution, energy resolution of different materials. So the high pure germanium detectors, of course, they have the best resolution. You can distinguish even very close lines with the very close energies. I would say that the cheapest scintillation detectors is sodium iodide has the worst resolution, but again, it's the cheapest one. So we can use it for dosimeters, for example, or if you analyze only one or two radionuclides with different gamma lines. Lanthanum bromide is better in resolution. It costs a bit more, but the resolution is better. Again, depends on what you are doing. Either you analyzing several standard radionuclides in your materials, and then you better use this lanthanum bromide if you have several lines that lays very close to each other. Again, high purity germanium detectors, they are perfect, but they normally used if you don't know the radionuclide composition of your material, then you really should use these high purity germanium detectors. If we compare it maybe in more understandable way, I took these pictures from Gabriel Lucas. So this is a comparison of different materials. So it is plastic scintillator. They have really bad energy resolution, but they have very good efficiency. So you can see your radionuclide, but you cannot really distinguish between them. So you can calculate the total amount of the radionuclide. With the sodium iodide scintillation, you have better resolution, so you can distinguish between different radionuclides. With the lanthanum bromide, you can see it even more clear. And with the high purity germanium detectors, finally, you can distinguish your radionuclide from other radionuclide. Yeah, it's, I think it's really a nice picture. So how we normally identified our radionuclides in the unknown sample. First, when we have this gamma spectrum and we are looking on some specific area in the spectrum, and we would like to know what the radionuclide are inside, we choose some energy interval, maybe more, maybe wider, maybe more narrow, depending on what you are doing currently. And we have this interval. And usually we say that the uncertainty of the determination of the peak position is something like 1 kiloelectron volts. And then our software gives us the list of the radionuclide, and then we should choose what is the correct answer. To do this, we can make quite a simple filtration by half-life, but there are two main cases. So let's start with this hypothesis number one. If we found the radionuclides that are present in our spectrum, and this radionuclide have short half-lives, the probability that these radionuclides are in our sample is very low, but we should check it. We should check this hypothesis that there are no short half-life radionuclide in our samples. So to do this, we can measure our spectrum again after some certain period of time. And if this peak area or count rate in this of these peaks does not decrease, that means that can mean, but not just the first approximation, that can mean that these short-lived radionuclides are not present in our sample. But if the intensity of these peaks decreases with time, as it should be due to the decay law, then we can say that, okay, these short-lived radionuclides are really present in our sample. But if these peaks are not decreasing with time, there is a second hypothesis that this short-lived radionuclide, they are progeny or daughter radionuclide of other more of other radionuclide with the longer half-life. Yeah, and either we can find this radionuclide, this parent or main radionuclide, and then we confirm this that our short-lived radionuclide it is the result of the decay of our our main radionuclide. Or if we didn't find the main radionuclide, then the presence of the short-lived radionuclide is not confirmed. There are just an example of these chains or even series of the radionuclides with the main radionuclide with long half-life, like titanium-44 with the half-life of 73 years, or germanium-68 with the half-life of, if I remember correctly, 270 days or something like this. And they have this short-lived radionuclide as the result of the decay. So again, if you found only scandium-44 in your sample, in your old sample, let's say, yeah, and you don't find titanium-44, that really looks very strange. Either it is a problem with the detection system, or you didn't find the titanium-44. So these two hypotheses. Of course, there are plenty of other radionuclides that are really daughter radionuclide in the very long chains that are started with the thorium or uranium isotopes, and these famous pictures. But again, if you find only, let's say, polonium 210, and you didn't find any other main radionuclides like radium-226, that may be a mistake. So you should check the correctness of your analysis. So this was filtration by the half-life. So it's very simple, and the first filtration of your radionuclides among the very long list of the radionuclides that the software can give you. The second filtration is by the number of the radionuclide lines. So here you can see an example of cobalt-57 and selenium-75. You can see that these two main lines of cobalt-57, 122 kiloelectron volts and 136 kiloelectron volts, is very close to 121 and 136 kiloelectron volts lines for selenium-75. But in this case, for selenium-75, fortunately, there can be another lines with good intensity. And if you will find them, then you can say that there is selenium-75 in your system. But how to say that there is no cobalt-57 in your system, if it can be present there? So to do this, you can, next filtration is by the ratio of the peaks areas in your spectrum. You can see that for selenium-75, the probability of these two peaks is different from the probability of these two lines for cobalt-57. Yeah. So for selenium-75, the 136 line is more has higher intensity, and for cobalt-57, the line 122 has the higher intensity than 136. So if you have, and by this moment already you should have the efficiency curve. By taking into account the efficiency of detection of this energy of the gamma quanta, you can calculate the ratio of the intensities of these two lines, and if this ratio of intensities is correlated very well with only selenium-75, you can say, okay, then there is no cobalt-57. Probably no cobalt-57. But if this intensity is not really the same as for selenium-75, then there is a high probability that you have also cobalt-57 in your system. But to confirm this, you should make then this destructive characterization, yeah, to be sure, if you have some doubts. Okay. So now about the characterization of the packages or the barrels with our radioactive waste. To do this, there are some techniques that use the scanning of the gamma radiation that goes from the barrel, and this scan is made during the rotation of the barrel, and it helps to identify the distribution of the radionuclide source inside the volume of the container. Because if you don't rotate, you will get the information only, let's say, from one plane of your sample. So, but there are several examples of different morphologies inside the barrel. Yeah, and you can see that this distribution of the components can be really very uneven, unhomogeneous. So you should get the collection of the scans at different angles to analyze the distribution, the spatial position, the geometrical position of this radionuclide source. And these measurements can be done in two main modes. It is either integral gamma scanning, when you have this wide open detection geometry, so you scan the whole barrel at once, or you have this segmented gamma scanning, so you have a collimated system that analyzes only a very narrow part of your drum, so you scan it at different positions in the vertical axis. So you rotate your drum and you collect information at some certain height. So of course, with this segmented gamma measurements, you improved the accuracy of the position of your radionuclide source. And yeah, these methodics, they are very well known and very well established. But of course, it takes longer time because at every position you have to make the whole scan of this of this DRAM. So depending on what is your desired resolution, spatial resolution, you will take, let's say, several scans for one DRAM. That means that you increase the time of the analysis by this number of scans. Yeah? And again, yeah, if in this case and in this case you have a rotating system, but in this segmented gamma spectrometry, you also should have this vertical position, the controlled vertical positioning of your detection system. Yeah. And there is an example from one of the technical reports how the information from this gamma scanning looks like. So it is a combination of the, let's say, optical image and the gamma scanning information from the system. So the next method is X-ray radiography. So in principle, it is the same method that is used in many X-ray analysis techniques, like in airports or in any industrial applications. So it very well established techniques with very good spatial resolutions up to down to 1 millimeter. And you can do it in 2D or 3D mode. And only the problem if you have heavy materials, when you will need not a soft X-ray, but hard X-ray source. And to do this, probably you will need some linear accelerators for electrons with high energy, so that this stopping radiation that will be produced by these electrons will have sufficient energy to be able to go through the sample. And we can use this X-ray radiography or tomography to analyze the density of our material, to understand what is the distribution of different components of the material inside the barrel or drum. We can analyze the presence of liquids inside this drum. And this is just, again, one of the example of this X-ray scanning. Yeah, I have better resolution on the screen. So it's a barrel, and I think you can see this distribution of the metal component inside this drum. So this technique is again very informative for classification or characterization of your radioactive waste inside the drum. And the last part of this presentation, it is neutron methods. Neutrons are very good in penetrating. So either, even if it is big particles, so they have a mass of 1, so it is almost 2,000 times more than electrons, but still they don't have a charge. So they can easily penetrate through the materials. And for example, 5 centimeters of lead layer reduce 1 megaelectron volt gamma rays down to 90%. So it's only 10% of the gamma rays will pass through this layer of lead, but 99.9% of neutrons will go through this material. So neutrons are really good in penetrating of the materials, especially with large numbers. So we can use it also for either neutron tomography, but also neutrons, they can be captured, or they can interact with the materials, especially with so-called special nuclear materials. So that means fissile materials like uranium, plutonium, etc. And due to this interaction, due to the fission reactions, other particles specifically for us, gamma quanta will be emitted, and we can detect this secondary ionizing radiation. So just an example, all of you know about this, that neutron interacts with uranium, and it goes through fission reactions, and it creates another neutrons, but also it creates fission products that are gamma emitters. And we can detect these gamma lines from the fission products and to analyze the presence of this uranium or plutonium or other special nuclear materials. So typically, this neutron detection system looks like this. So there is a source of neutron. It can be either just a radionuclide source of neutrons, like plutonium, beryllium source of neutron, or it can be, in principle, the pulsed neutron generator, like then electrons interacts with wolframium, for example. It creates some neutron flux. So there is our sample, and all this system shielded with the polyethylene materials or some naphthalene materials, so where we have a lot of hydrogen, or let's say light atoms, because these atoms they moderate very efficiently the neutrons, so they decrease the energy of the neutrons very efficiently, and then these thermal neutrons are caught by cadmium or boron or other materials that can catch neutrons without any without any consequences of the nuclear reactions, let's say. So it is a scheme, again, from the same source. Again, this the drum that is analyzed, it is the source of the neutrons, and this shielding around the system. Again, as far as neutrons, they have very high penetration ability. That means that we need to build this huge shielding around this detection system to avoid the extra irradiation of the personnel. And again, why these light atoms are good in moderating of neutrons, because if alpha particles, beta particles, gamma radiation, they efficiently interact with the electrons, it is not the same for neutrons. Neutrons interacts only with nuclei, and if it is not a nuclear reaction, then it is just a scattering, mechanical scattering of two particles. And one of the example to imagine what is better for moderation of neutrons, you can imagine the ball for bowling, yeah, this heavy ball, and the ball for ping pong, for table tennis. Yeah, and if you will drop this small ball on this heavy ball, that means that your ping pong ball will just scattered without losing any energy, because it's very heavy. So there is just scattering without any change in energy. But if you have two small balls and they interact, then the energy of these two balls will be splitted between these two masses, because they have very close masses. And thus, if you have one proton, hydrogen, yeah, it's proton, and you have the same mass, neutron, very close mass. Yeah, it's difference on the in free or something like this masses of electron. So then you have a hydrogen that that rest. And then you have a neutron that goes with the high energy, and when they interact, the energy of neutron split it between proton and neutron, so the neutron loses its energy very efficiently. Half of this energy just lost and given to transferred to the proton. So if you have the close masses, then this splitting of energy or transfer of energy is very efficient. That's why for moderating of neutrons in nuclear reactors and also here in this shielding, the light elements are used, and the main element is hydrogen. So you need to have some shielding. Either it is polyethylene, or it can be just water, or something else containing a lot, or wood, or something that contains a lot of hydrogen atoms. And then these neutrons are moderated, so they stop, they have thermal energy, then they can be catched by either cadmium or boron. So this shielding can be quite huge to moderate neutrons and to catch them. So this was example for detection of the nuclear materials, so the materials that can go through the fission reactions due to the action of the neutrons, but also the neutron can activate the stable nuclei. They can convert them to unstable nuclei, and thus we can detect the gamma radiation that goes from the resulted radionuclide. So there is a general scheme. We have a target nucleus. It can be stable nucleus. Then after neutron interacted or captured by this nucleus, the compound nucleus either immediately release the gamma ray, or it releases the gamma ray after some time. So, and in the first case, we are talking about the prompt gamma activation analysis, gamma neutron activation analysis. Yeah, we analyze the gamma rays that goes immediately from this compound nucleus. Or for some purposes, yeah, we when it is delayed gamma irradiation, we are talking just about the neutron activation analysis, very popular for analyzing the micro quantities of some metals like gold, for example, in ores. Very sensitive method. You can detect something like nanograms of gold inside the sample. So it's very good technique. So, and with this prompt gamma activation analysis, you can detect even light elements. So actually, you can analyze the chemical composition of your sample inside the drum. So without taking the samples out and performing the destructive chemical analysis. So it's a very powerful technique, but again, to do this, you need a source of neutrons and all this shielding. So it's a very expensive technique, very powerful, but expensive. Okay. So, and just few words about other non-destructive methods. One of them, it is so-called track analysis. Either it is track analysis using the plastic detectors. So you put your sample, for example, it's just the soil containing some hot particles. Yeah, you just put it on these plastic detectors, wait some time, and then you analyze the distribution of the defects in this plastic detector. And these defects, they show you the interaction of alpha or beta particles with this material. Or you can use so-called digital methods, digital radiography methods that can show you almost the same information. The main difference between these methods that plastic detectors they can be used only once. So because it's just a mechanical damage of the material that you analyze with the microscope, and digital screens they can be used many times, multiple times. I don't know, 100 times. Also, the good point for these plastic detectors that the defects that are produced by the alpha or beta particles, they are not healed, so they stays there for eternity, for forever. Yeah, if there is a mechanical damage of the material, it will stay there forever. But these digital plates, they have a limited storage time of the defects. It only lasts for, let's say, 3 days or maybe 1 week. After that, all the defects are gone, so you cannot measure your samples for a very long time. For example, if you have very low activity, you can put your sample on plastic screen and leave it for 1 month, for example, or something like this. Any event, even single event, will be detected in this system. But for digital radiography, you can put your samples, you can leave it maximum for 3 days. After that, these defects will be annealed just by natural processes. These radiography techniques also very useful when we analyze either living organisms, for example. We don't need to kill them, let's say. When we're talking about the plants, for example, we can see the distribution of the radioactive material inside this living organism. But also here is an example of the sorption of the radionuclide on the surface of the mineral rock. So it was done to study the possible migration pathways of the radionuclides in the future site of the final repository of radioactive waste. And radionuclides were sorbed on this material, and you can see that this sorption is very uneven. Yeah, so there are only some spots, some minerals that are responsible for the sorption of the radionuclides. Yeah, and we can see this special distribution of the radionuclide. We can compare it with the optical image, and we can analyze what are mineral phases here, and to take into account this information for further modeling of the radionuclide migration. And again, we can classify this detection system either by the method of reading information or type of the registered radiation, alpha, beta, or combination of these types of radiation. It can be reusable or not. And for plastic detectors, for example, we need to make some chemical operations to see these mechanical defects, or it can be some photochemical processing, or even without processing. And just few words, final words about this digital radiography. So it is based on the special plates that are the material of these plates, this complex mixture of barium fluoride bromide with some doping by europium. And when europium is interact with ionizing radiation, it goes to the higher valence state, and then with the irradiation with the laser, it goes back to europium +2 and irradiate red photons. And there is another example of this digital radiography. So it is leaves from one of the plant that was located in the contaminated pond. I think it is from Mayak plant. And we can see the distribution of the radionuclide on these leaves. Sometimes we can find the hot spots, so it's just dirty soil on these leaves, and we can analyze it. So these methods they are really good when we are working with the natural samples and can be very useful. So thank you for your attention. If you have any questions, we have time. If not, we can, yeah. Yeah.
Thank you. You said something that there are some calibration sources that can be used in order to simulate the big drums.
Yes,
of the
yes, yes,
radioactive
yes,
waste.
yes, yes.
They
There are,
put inside some inhomogeneous patterns. And,
yes, 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 yes.
okay.
There are normally some balls, so with some known geometry to calibrate the system.
Okay.
Yes, yes. It is similar to the medical application. They also have these phantoms of the human body with some sources with known geometry, put it inside this phantom. So more or less the same, but the shape is just drum.
Okay.
Yeah.
And another thing is at this final slide with the plant,
Mhm.
how you want to distinguish between the radioactivity that is contaminated on the leaf and the radioactivity that is in the leaf.
Yeah, before this examination, we washed lifts. Yeah, so and yeah, to wash away the outside contamination. Yeah, and then we can say that it is inside.
So that is the scintillations from the inside
yes,
of the.
yes, 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 yes.
And why we are observing these differences between the center and the. Have you any idea?
I cannot say at the moment. I'm not biologist, but yeah, they investigated. I think it's due to the age of this leaf, but I'm not sure.
Thank you.
It's just an example what we can see from this technique. Yeah. Any other questions? If not, then thank you, and we have some time.
So good morning, everybody. It's time to start our lecture. My name is Anna Semenkova, and today I'm here to talk with you about engineering safety barriers providing the isolation of nuclear legacy facilities. Here on the map, you can see the location of different nuclear power plants, deposits of radioactive waste, and objects of nuclear objects. And the bigger problem is how to store them, how to make it safe, how to make the storages of them safe. Today we will talk not only about the nuclear legacy facilities, but we will also discuss the problems of engineering barriers on deposits of radioactive waste and repositories. The difference is that nuclear legacy facilities, they're rather old objects and that were created when no information about best practice how to store them was known. So, but nowadays we have new ideas, new scientific researches that let us make the engineering barrier materials safe and to obtain the safety of the objects for 100 years and 1,000 years. So sometimes it's useful to take the practice from to take information that were obtained from was obtained for creation of different deposits or repositories and to use them for nuclear legacy facilities. That's why today we will talk about different topics. We will start from discussing requirements for barrier materials. We'll talk about scientific foundations for the selection of barrier materials. And at the end, we will talk about experience of engineering safety barriers that were applied for installation of nuclear legacy facilities. So here you can see the types of radioactive waste. That's an IAEA classification, as you know, I'm sure. There are different types from very low-level waste, low-level, intermediate level waste, and high-level waste. Waste. So depending on the period of half-life and the activity of the waste, different types of barrier materials are needed, and the location of the repositories differs from the, if in case for very low level and low level waste, they can be located near earth, near ground level, and with increasing of the dangers of the radioactive waste, the repositories going deeper and deeper. For example, for low level waste, it can be about 10 meters, up to 10 meters. For intermediate level waste, they should be in depth up to 100 meters. And for high level waste, the depth of the repository is from 100 meters up to 900 meters. So the first of all, I should mention that the multi-barrier principle should be included for creation of all repositories. Here's the example of low-level waste repository. Here you can see the containers with the radioactive waste, with solidified radioactive waste. Usually it is not in liquid form. If it is firstly it was in liquid form, they have to be put in matrix and solidified. And in solid state, they are in special containers. They are located in the deposit repository. And this is the first difference between repository of the new created repository and the old facility nuclear plant. Because here you can see only in radioactive waste only in containers, but in case of legacy sites, they can be in different forms not only in containers, maybe even without them. So first of all, our containers, then special buffer material that between containers, that is located between containers, it can be made from different materials. We will discuss it later. Then here we can see the concrete walls. It is the kind of building in which our containers are located. And after that, the special lock Usually it is made from clays. It's a thickness about 1 meter. And here it is also can be underlying cover. And on the top of the repository or any kind of legacy site, it also should be covering layers, several layers, depending on the type of the waste and so on. And it includes our concrete walls on the top, the clay layer, and different layers of crushed stones and soil on the top and so on. So the idea is that the idea of multi-barrier principle, that in case if even one barrier will be broken or damaged or something will happen with it, the next layers will prevent radioactive material leakages into the environment. So that's why the more dangerous radioactive material we have in our repository or nuclear legacy site, the longer half-life they have, the bigger activity, the more strict rules we have to be used for the choice of the barrier materials. So what is the most dangerous in case of any repository or nuclear legacy site? The most dangerous if we have water in our repository. I will call it repository for shortness, okay? But it means that repository, deposit, or nuclear legacy site, okay? It is for all of these objects. So the most dangerous situation is if we have water in our repository and we have water that is going out of the repository with our radionuclides. If we don't have any water in repository, everything is safe. Our radionuclides will not move outside. Maybe just a little bit as gas, but it's not a big problem actually. The most dangerous situation is that we have water intrusion inside in case if there's rain or a groundwater get inside or something happens, or maybe leakages outside due to the degradation of our matrix where these radionuclides are located. So if we have any leakages, they will go outside, they will contaminate groundwater, and they will go into the river, seas, and so on. So, and human and animals, the human body will be damaged by the radionuclides. That's the most dangerous situation. That's why our task is to avoid any leakages any leakages from the repository. So here are a few general requirements for engineering barriers. First of all, engineering barriers have to limitate their contact of radioactive waste packages with environmental waters. Then they should prevent the destruction of radioactive waste packages under natural or technogenic impacts. Then barriers have to prevent the destruction of radioactive waste packages under the influence of surrounding rocks or soils. And of course, it should limit the radionuclide distribution into the surrounding rocks or soils within the time scale that is established in the project. For this first requirement, it means that we have to study our filtration, diffusion, and migration properties of the surrounding buffer material. And the last one, it means that we should also know our absorption properties. That's the task of the scientific task that we also trying to solve in our lab. Here's one of the examples of the multi-barrier system that has to solve the problem of leakages, and all the materials are suitable and for these requirements. So we can see that this is the example for high-level wastes. So where we have the most strict rules and requirements for the materials. So we can see here different barrels or blocks in the cementified material with that contains radioactive materials. Then we have a cement buffer. Usually it is Usually, it is known that better to use clay materials, something like it. Maybe even compressed clay materials. And after that, the last barrier is host rock. Usually, because high-level waste are located in repository are located in rocks system underground, deep underground. And here's again the low-level waste scheme. So you can see that we have the same situation. We have different barrier materials, different barrier systems. First of all, we will talk about the first barrier. It means that the container, we just briefly talk about it, because for low level and intermediate level waste, we have two different types of containers that are made from concrete or made from metal. So when we have to choose our type of container, we should take into consideration the specific activity of waste, the total activity, the alpha, beta, gamma activity of emitting radionuclides in the packages, the radionuclide composition of the waste, the equivalent dose rate from the package, the surface contamination of the package, and also we should remember about the size of the container and the mass of the waste that could be located inside them. So here's the example of non-returnable protective container with concrete inside. So you can see the size of them. And also I remind you that all containers, they contain radioactive materials in a solidified form, not in liquid. And here are metal containers to collect and for intermediate storage of radioactive waste and for transportation. Sometimes it is also used for the storage up to 50 years. What's going on? So these containers can be used for storage or for disposal of the radioactive waste up to 50 years. And here just several examples of size of containers. Here's the effective capacity, how many meters, cubic meters of radioactive waste they can be inside, and the empty weight and the weight with the radioactive waste, and the size of the containers. And it is also, I also want to mention that the difference between containers is also in which form waste should be located in containers, in barrels, just in bulk, or in some backfills, or anyway. So this is the parameter that influences for the choice of the type of the container. So the next level is our buffer material and our concrete walls. Oops. Let's start. So concrete, from concrete we make our walls, our buffer materials, and sometimes our containers. Concrete is a material that is made from cement, water, sand, and some aggregate, and sometimes even some special adjectives to make it better properties. But there is a big problem, because you can see here there's a picture of concrete blocks. There are pores and small cracks. This is a fresh material. During degradation, during the impact of radiation from the waste, the concrete material can be damaged, and the damages become rather fast in first decades, from 10 up to 50 years. First cracks can be observed in concrete, and it's not very good for our deposit. So then another type of material that also can be used as buffering material and also as underlying or covering screen of a repository, it is natural clays. There are many types of clays. Here we can see the usual structure of them. They are made from aluminum and silicium octahedrals and tetrahedrals. And inside here, they have any type of cation. Usually it's 2-valent or metals in valence 2 or 3, like magnesium, aluminum, potassium, something like it. But in some cases, and here I think all you know how does the clay look like. But sometimes when we talk about our requirements for the low permeability of water, limitation of water flow, we should know that about advantages of one kind of clays that is called montmorillonite. This type of clays, they have interlayer cations or water molecule in their structure, and they can absorb water or any type of cations in this place. And it is very suitable for our requirements. Here's another picture of the clay structure, and here's the place where water molecules or cations can get in. And there, if we have water here, because if we have water intrusion in our repository and water intrusion in our clay buffer or clay, I don't know, clay walls or something like it, it means that water gets here in the structure and it is bonded to the structure of clay, and this water cannot go through the material. It is stabilized, and we don't have we prevent water flow in our repository. That's the main advantage of the clay material of montmorillonite. Here it is mentioned that bentonite clays. Montmorillonite, the difference is that montmorillonite is a pure clay mineral, but in nature we have always mixture, and if in our sample we have more than 50% of montmorillonite, that kind of clay is called bentonite clay. And also one of the advantages of the bentonite clays or montmorillonite mineral, that there are different types of sorption sites for sorption of molecule of cations of our radionuclides. There can, and different types, they have different types of sorption sites, and they have different nature, and it means that they're suitable for different types of cations that can be bonded by different reactions. Here you can see that plus, it means that on the top of the clay particles, they are localized, the plus charge is localized, and it means that the negative charge is localized here, and the positively charged cations can be bonded with the top of the clay, and they also can be bonded in the interlayer space with where also molecules of water are included. And here we can see the on the bonds of the particles another type of places to sorb with aluminum or silicium in the end. And for all type of materials, there are different. We have several objectives for the type of materials that are very suitable for our purpose of our safety barriers. So the objective of using of the bentonite clays, all totally, is first of all to stop or minimize of leakages or contaminated beyond the barrier. So it means that such processes as filtration and diffusion have to be determined, and sorption capacity, and we will talk about it later. After that, we should take into consideration that for bentonite clays, it is not impossible to formate the rapidly migration forms, but they're not very. They will not give the additionally migration forms for fast migration of radionuclides. So of course, one of the big advantages of clay materials is that they're stable for long periods of times. Clays are there more than 1 million years old, so they will be stable not for 10 or 50 years like concrete, but they will be stable for 1,000 years, and it's a big advantage. So they are safe in case of fire explosion, and they're not toxic at all. And of course, they have very accessible cost, and they are rather available in different countries, in different parts of the earth. So that's why usually first in the beginning of the nuclear century, natural materials like soils or sands were used, but nowadays we recommend to use clays and bentonite clays especially. Based on the advantages of bentonite clays, there is a kind of material that called bentomates were made. They're used for underlying and covering screens, and they're very easy to applicate them. The bentomates are made from two layers of geotextile from supporting and covering geotextile, and between these layers, the granulated bentonite is located. So in case if we have water leakages, bentonite will stop it. And here are several scientific foundations for the selection of barrier materials that we will discuss next. We should first of all think about the forces that drive the migration of the radioactive wastes of radionuclides. First of all, the filtering of atmospheric precipitations, influx of moisture or to the surface as a result of evaporation, thermal transfer, something like it. After that, we should take into consideration the water movement on the surface, diffusion of cations and anions, and transmit of colloidal particles. So I also remind you that our purpose is to provide the mass transfer only by one mechanism, that is diffusion, not filtration, because filtration, it means that we have a water flow that moves through our barriers, through our repository. And it means that our radionuclides will get very fast into the environmental, and that's the most dangerous situation. In case of diffusion, we have a very slow process of intrusion of radionuclides outside, and we'll talk about it a little bit later. Here are some advantages of and features of application of barrier materials. Here in the picture, you can, maybe it's not very well seen, but please pay attention for the picture, because here you can see the unique ability of swelling. It means that water molecules, when they come and get inside the interlayer space, you can see here that the sample, it gets bigger, it is enlarged, because it takes water inside, and there was water, and now we can see that here is the quantity of water was became less, but the size of the clay bentonite clay was enlarged. It means that water gets inside the structure and is very, 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 very useful for us, because it stops filtration. It can stop filtration and provide only by diffusion absorption. Here you can see water gets here. Because clays, they're made of many particles, and they have about 10 or 20 layers of interlayer space just in one particle. So many particles, so that it can take inside a lot of water. Here's the picture of swelling of bentonite. Here's the example of the bentonite particles. It is mentioned as small layers and interlayer space. Here it is. So here you can see that just usual aggregates of clay particles without any water. They're small and nothing special. Here you can see the water intrusion, and the particles become bigger. They take water inside, and they getting bit larger in their size. Here you can see the example that not only montmorillonite is a clay, just a clay. Here you can see the different clay materials that differs by interlayer space and lower charge that is located here, that makes possible to sorb any cations. So we can see that depending on the lower charge or interlayer space, that is the increasement of these parameters, there's materials with the smaller and the larger interlayer space and lower charge. They don't have any swelling ability, but the montmorillonite has the best parameters, and also rather good parameters can be obtained for mixed layer clays of different composition. You can see the difference in localization of the charge in these materials. So let's talk about diffusion a little bit more. I will remind you that diffusion means that the movement of the molecules, in our case, it means of molecules of radionuclides, that movement from a region of high concentration and to region with a lower concentration, it is obtained just by a concentration gradient without any water flow or something like it. So here's the example. Here's the picture of rocks. How does it look like and how does diffusion goes? It means that diffusion goes very, very slow just by the gradient of concentration through the pores into the clay material. So there's no just straight road for radionuclides. They go very, very slow through diffusion double layers downstairs with the water. And here's the example of diffusion experiments that we provide even here. We have two bottles. In one, we have liquid with that contains radionuclides. In another, we have a pure solution, the same solution with the same composition, but without radionuclides. And here we have, here is located a sample of clay that we want to study. And we have, using the pressure, we study how fast will we find radionuclides in the pure bottle with water. And after that, we make a graph with mass flow and how fast does the radionuclides go through the sample of our clay to the bottle with a firstly clean solution. And here are the results of this experiments of the montmorillonite. It shows that the presence of montmorillonite gets the diffusion coefficient smaller. Than more montmorillonite in our sample we have from 0 to about 1 we showed. Then smaller diffusion coefficient. It means that then more slowly our radionuclides go through the sample, and it means that the sample has better parameters. So we can see, for example, here we studied a tritium and chloride anion, and you can see that especially for anions, the presence of montmorillonites getting the migration very, very slow. Also, I wanted to mention that the density of the sample also influences on the diffusion coefficient. When the bigger density of the sample we have, then slower diffusion coefficient we have. It is very important in case of slowly sorbing anions, radionuclides in anionic form. And so here we can see the another pathways by which control the migration of radionuclides into the environment. Here's M. It means the metal, or any cation. In our case, it means that it is radionuclide in cationic form. So first of all, it can be sorbed on the particles of clays or concrete, on something what we have as a buffer material. After that, it can make aqueous complexes with carbonate anions, phosphates, nitrates, and so on, what we have in our solution. Then cations also can precipitate as a pure phase. It is not very common, but in case if we have high concentration and favorable environmental condition, it is also possible. And cations, our radionuclides can also co-precipitate with any other material, with colloids, with I don't know, anything that we have in our system. And if we have precipitated radionuclides, it is very good. It is very favorable, because with this part of radionuclides, they will not go further. They will stay just somewhere close to the repository. And also the radionuclides, that is very bad way. They can sorb on colloids, small colloid particles made from concrete, from clay, from something else. And these colloid particles, they have very small size, but they can sorb a big quantity of radionuclides due to the big charge on their surface, and then can migrate rather far. Maybe you've heard about cases in the United States when there was the plutonium particles were observed in several kilometers far from the place that far from the deposit. Several kilometers, not meters. Kilometers is very far, and it was and this transport was devoted just to the formation of the colloid particles with of plutonium with the sands that were located in this were located there. So this is very unfavorable way for us, but it happens. So it is necessary to take into consideration not only the isotopic composition of radioactive waste, not only the kind of emitting alpha, beta, or gamma. It is also important to take into consideration the chemical composition of the waste. It means that different types of elements, they have different behavior. If we have cations and anions, they have very different behavior. And even cations in different oxidation form, their behavior differs much. And it's necessary. And also we have to control the chemical form of elements. It means that even if we have, for example, uranium in our waste, uranium in environmental can be observed in several valence states. Usually it is uranium-4 or uranium-6, but in case if uranium-4 is very stable and it precipitates and it usually doesn't move far, uranium-6 uranyl cation, it is very it can move very easily, and it is very important for us if we have if we have to make a new engineering system for our legacy site or for deposit. We have to, first of all, we have to know what do we have inside, and in which form will we have our components in case of any leakages, because environmental waters, they can differ and they can influence on the cation and the form of the elements. I talk so much about these problems and these points because before creation of any type of barrier, you have to demonstrate that the kind of barrier will provide all these functions for the long period of time. It means that for 50, 100, or 300 years, you have to provide that the material will be stable, that it will provide safeness, that radionuclides will not go outside. So we have to obtain a license for your deposit, and you have to demonstrate that diffusion, sorption, I don't know, filtration, they will not these parameters of the material that you choose, that they're suitable for hundreds of years for exploitation of the barrier materials. So also we have to take in consideration the composition of solution. For example, is pH, the presence of microorganisms, the cationic and the anionic composition of the natural waters in the place when our facility or nuclear legacy facility or deposit is located. Here's the example of two natural waters, and you can see that in Europe, and you can see that the pH differs much from 7.3 to 9.7, and it is a big difference, and it is very important in case of we talk about sorption and diffusion of cations, especially of cations. After that, it's important to know if it is aerobic or anaerobic conditions. Usually it is important for high-level waste repository that are located deep underground and without any oxygen, because the presence of oxygen or CO2 from the oxygen also has an impact on the sorption of radionuclides and in the form or the chemical form in which our cations will be in solution, not only cations but even anions. Then we should take into consideration the temperature in the deposit, because during the decay of the radionuclides, temperature may increase, and in case of high-level waste repository, the increase of temperature may be up to 100 degrees. And of course, we have to look for the composition of soils, of our materials, of our barrier materials. Are they suitable for formation of colloids? And because it is also important that the composition of solution also influences much on the speed of formation of colloids. How fast will they form? How stable they will be on their size and so on. Yeah, I think it is the example of the increase of the temperature in the buffer material close to the container in the high-level waste repository. For the first meter, the temperature will be about 100 degrees. So now we will talk about sorption. That is the process that also is included into diffusion, and not only in diffusion, but even if our migration is was not localized just by the diffusion process. So for the sorption, we should take into consideration the mineral composition and the aerobic anaerobic composition, also the solid composition and the temperature. For example, here's our uranium. You can see that the difference in pH influences the form on which uranium is stable in the solution. If we have up to pH 6-7, I think, here we can find rather good sorbed uranium cations. But in case if we have uranium carbonate in pH up from 9 to 10, they're very low, they're very badly sorbed. So this is for the question of the composition and the pH of the solution. Difference of pH of the solution of the groundwater can influence not on the sorption and diffusion properties of the cations, not only uranium. Also, the presence of different materials, such as metal containers, can change the oxidation state of different radionuclides. Here's the example for uranium. Uranium from oxidation state 6 can get into the oxidation state 4. And the example of the influence of temperature. Here you can see the influence, I think it's example for europium, not for uranium. So with the increase of the temperature, sorption can get higher. So it means that we have high sorption not only at pH 8, but at pH 4, from pH 4 to pH 10. It's very good. In case of europium, maybe it's not the influence of temperature have to be studied for all radionuclides and cations that are located in our repository. So here's the example of just several small examples just to show you that sorption differs much from element to element. Here's the sorption of europium, that europium can sorb by 2 mechanisms of ion exchange on the surface and interlayer space, and by the mechanism of complexation on the hydroxides located on the bonds here. So you can see for one element, 2 mechanisms of sorption are available. It is not for all suitable for all cations. And in case if we know that our cation sorbed, our radionuclide sorbs by the mechanism of complexation, it is known that the surface area of the barrier materials, in our case it is different clays, influences much on the sorption. With then bigger surface area we have, the bigger sorption we have. So you can see it here. The next example is the influence of impurities. As I already mentioned, our barrier materials, and our clays, it is natural material, and it have a very many additivities. It is mixture of different components, and in case or if we have some goethite that was observed in one of the clays from India, sorption of some actinides getting higher. In case of neptunium, you can see that sorption on the sample that has 3% of goethite and its composition is much higher than on the purified from goethite sample of the same clay. So you can see just 3% gets desorption much higher. It is very useful in case if you know that you have some not very good sorbing element in the composition of your radioactive waste. If you know that, for example, you have neptunium or something like it that has bad sorption properties, but you know that you can make some small additivities of special material. For example, goethite can be added for just for a natural clay that doesn't have it first of all in its composition. So you can make some additivities and you make the absorption properties of your clay much better for the special cations. Here's just the results of modeling of the sorption of natural clay that contains goethite and the purified sample. And the modeling shows that that really the goethite is the material that provides the better sorption of neptunium in this case. If we talk about cesium sorption on clays, the cesium can sorb just by the mechanism of ion exchange on the in the interlayer space and in the surface of the clay particles. And you can also note that here that the sorption parameters is distribution coefficient. They differ much for different clay samples. Here you have a colonite, green, marked by green color, that has no interlayer space. And you can see that sorption is much smaller than in case if we talk about bentonite clays, and if we increase the presence of montmorillonite in our mixture. Here you can see the samples that contain 99% of colonite, 70%, and the sorption becomes bigger, and it means that the rest 30% is montmorillonite and 70% of bentonite and pure bentonite. Here the difference is not very big, but it also exists. And the same situation you can see here in the whole pH region. We can see that sorption on colonite is much lower than on bentonite, and with increasing of bentonite composition in the bentonite content in our clay, the sorption of cesium increases. And here was a big idea to check how to compare the sorption properties of rather common known clay deposits all around the world. Here's in the United States was a sample MX80 that was used for main researches, and in Europe it is clay Fabex and so on, and clays from Russia and the nearest countries that are available to use in Russia Federation. And here are the results of sorption experiments. You can see that also that all these clays, they are bentonite clays that have more than 80% of montmorillonite in their composition. Not a lot of kaolinite and so on. But you can see that even if they have here, these samples have very similar content of montmorillonite, but the sorption also differs. And the same in this slide, in this picture. So it means that different deposits, they have different clays, they have different characteristics, and that should be also all considered during choosing the material for the material for the creation of barrier. Excuse me. And here is the idea why this difference can be observed. This answer is the presence of the negative charge in the surface of the clay particles. The lower charge was observed due to the isomorphic substitutions in the clay structure here. And the bigger, you can see here that the biggest part, then the bigger charge, it is tetrahedral charge that's located in the tetrahedral here, then it is bigger, then higher sorption of the cesium can be observed. It's just an example for how can different deposits influence the absorption of different cations. And after all, when we provide our absorption or diffusion experiments, we can make a special modeling that can prove us or anybody else that our material has a good absorption diffusion properties, and it is possible and it's recommended to use it in case of engineering barriers. We also have to into consideration the different characteristics of barrier materials. First of all, it is technological characteristics that we should provide, that the kind of material can be used in engineering criteria, that it has suitable granulometric chemical composition, density, surface area, and so on. And that they have swelling pressure, permeability, and water separation for deformation. And of course, we have to take into consideration the functional properties about which we talked a little bit. Absorption, desorption characteristics, diffusion, swelling, content of organic matter, collidation, and so on. And here are just several parameters that were discussed for using of clays in case of high-level waste depository. And these parameters are not suitable not just for the high-level waste repository, but also for all nuclear legacy facilities and deposits of low-level or intermediate-level waste. So firstly, we should mention that material is available, or we can bring enough quantity of this material to the place where the facility is located. So if we use any kind of repair material, like if we have to make a mixture of the clays or something like it, we should check if it's technologically possible to manufacture this quantity of the material that we need. Of course, physical and mechanical properties and the form factor, that if for intermediate and high-level waste, it's better to use compacted blocks or any materials from bentonites, like bento pellets and something else. And the same situation with bentomates that can be used for all types of the underlying and covering screens in our low-level wastes, bentomates. So in which form factor will we use our material? Then we should check our water permeability, the water permeability of the material, the diffusion properties, and all the absorption properties, and gas permeability. In case if we have gas in our deposit, it should not be located. It has to have possibility to go outside, because otherwise we will have any bad situations. Also, it is not very common known, and also not always these researches are made, but we have to think about microbiological transformation in case if even of high-level waste repository or in low-level waste that are located on the ground level. Microorganisms, they can transfer our cations, ions on different forms. They can influence on the migration of these elements. We should think about possibility of corrosion if we have metal containers in our repository. We should think about thermal conductivity of the barrier materials in case if we have we may have high temperatures in our object. And of course, any physical and mechanical properties like density and so on. Also, that it has to be mentioned, the influence of conditions, as we've talked about, the impact of other components of barrier. For example, if you have metal or concrete containers, how will they work on the close to the clay buffer and so on. If we talk about clay materials, we have on the top of the that are located on the top of the deposit. We should think about erosion that is also possible in this. So here we can remind the requirements for the barrier materials, but I think that I've already mentioned enough about it. I also want to say that nowadays we don't have any specific requirements for the barrier materials in case of low-level and intermediate-level waste deposits, just for the high-level waste deposits, where a bigger quantity of works were performed. But we think that we can be guided by the results of so many works that were prepared for the high-level waste repositories. We can be guided by these results to provide our works on choosing the barrier materials for nuclear legacy facilities or for deposits of intermediate and low-level waste. Nowadays, from 2022, Moscow State University and our department is the scientific head of the big program of the scientific and technological support of works to substantiate the selection of barrier clay materials that are used in the implementation of projects in the final stage of the life cycle of the nuclear power facilities. So not only Moscow State University, but also a lot of other institutions and organizations participate in this program here, just mentioned just a few of them. And this program has to create and develop a unified system for the selection and the use of barrier clay materials. So the idea of this program is to create a big database. Nowadays, it contains about 43 prospective barrier clay materials. And to make this database will contain a lot of parameters that are needed to justify that the barrier is suitable for the long-term terms. So during the program, also the special demonstration benches for engineering safety will be made and have been made to provide the fulfillment of the declarated functions for the creation barriers on the in large scales. We also developed the methodological guidance to conducting predictive modeling to substantiate the safety of engineering barriers with the bentonite glaze materials, and we also developed the regulatory documentation. So here the required material quality indicators that will be included into the database. It includes not only the mineral composition of the clay, but also the chemical composition. We determine the content of organic matter, the cation exchange capacity, the filtration coefficient, and the diffusion characteristics, and so on. And parameters that we call functional and technical parameters that will make suitable the using of this material in future. And we have some time to talk about experience of application of engineering barriers on nuclear legacy facilities. Here's the example of disposal of high-level waste that is deep underground and that has, I think I'll pass it. Yes, and here's the idea. I've told you that a lot of scientific researches were made in case of high-level waste deposits, and here you can see that the number of publications is more than 1,000 works. If you will look for a kind of barriers for intermediate level waste or something like it, you will find just maybe 10, less than several 10, 20, 30 publications about it. But here we can have a big quantity of the publication. That's why we can be guided by the results that were obtained in this area. So, and here's the example of very low level waste that is that it can be made like trenches. Here is in Japan, just trenches that has some blocks, some concrete blocks, and the bentonite sheet on the downstairs. And you can see here that we don't have containers with the waste, just something, plastic bags, something like it. It's very low level waste. It is the example from Japan, and on the top they will be filled with sand and some kind of buffer material and covering screens on the top. And here's the example of Sweden. You can see that they have a concrete blocks on the floor, and then containers, just usual metal containers. I don't think that is any special for radioactive waste made, and you have several layers of the bentonites and gravel on the top. Just everything is very simple, very cheap, and very easy to make. Here's the repository of short-lived low and intermediate level radioactive waste. Here's the example. You have concrete walls where our containers are located. We have a special building out on the that surrounds our containers, and they made a special bentonite underlying before creating this building. And in Belgium, there was the several sites for the storage of radioactive waste, and they are. Here's the example of Dessel. So they have concrete walls concrete buildings where their containers are located. After that, they have a mixture of sand and clay on the top, and then they have several layers of concrete and soil on the top, and it also here can be used bentonates. In Japan, there are several places where deposits are located, and different types of deposits for low level and intermediate level waste. They have a different construction on the earth, under deeper on the downstairs, and that are located near the ground level and deeper. So they have the same construction. They contain containers with the radioactive waste, and then in case of intermediate level waste, the space between containers is filled with buffering clay material, and they have several layers of soil and soil with bentonite, and so just usual soil on the top of the deposits. And here we can see the first example when the deposit was closed and the waste from the deposit was removed to a new place. In Hungary, in 1960s, there was built a small deposit for radioactive waste that is called Solimar State, and it was located very close to the capital of the country, Budapest. And after 20 years of the work, it was found that this place is not safe, that there were a lot of leakages, and it was due to the closeness to the capitals, it was very dangerous for the human. So the decision was made to remove all the waste to another place. So in the 2000s, the new place was built for the final isolation of waste, and all waste were removed there. And after it was about 5,000 cubic meters of radioactive waste that were located in trenches and shallow wells there, here and here. But in 2012, this place was fulfilled, and the new deposit was built for low level and intermediate level waste. It is located in a granitoid massif and in a big depth. But here we can see that in case if we cannot if we cannot create new barrier systems, new engineering barriers for all nuclear legacy sites, sometimes it is even possible to remove the dangerous radioactive waste to another place. In some cases, it is possible to create a new engineering barriers. And here's this briefly will tell you there's Sellafield, and here was a very big, disappointing experience of using of concrete in a case of a barrier material, because after 10 years after the creation of the deposit, it was found that there were big boreholes and leak in cement, and there were leakages to the river and finally to the sea for the leakages of radionuclides. After that, the new building was made. All wastes were removed to a new building located in the same place. But after about 15 years, they've opened it, they checked it. It's always necessary to check if everything is okay with our deposit. They checked and they found that the metal containers were corrosed. The concrete has again any kind of trenches, and again they had leakages. It was happened at about 10-15 years of the exploitation of the object. So, and just few examples of conservation of very special radioactive waste storages. Here's the example of conservation of industrial uranium graphite reactor. It was impossible. It was very hard to remove everything from there and to move somewhere into some existing deposit. So the decision was made to backfill the reactor with a barrier mixture, and it is named that on-site disposal. It means that the reactor was demolished. The top part of the reactor was demolished, and the reactor part was full filled with a barrier material that contains clays. Here's the example, the picture of the reactor before, and here is the picture how it was deposit. I want to mention that they have a big size. It's about 50 meters length and 50 meters 40 meters, so here, and there were a lot of rooms and different type of places, and it was not very simple to fulfill it with the clay barrier material. So there were experiments were made, and here is the demonstration stand. It has about 6 meters high, and the clay material was colored into red. It is the natural color of the clay, and here it is some of the clay was colored into red, and it was checked that the clay cannot be located just in the place where you put it, but it goes to the closest places. So it was shown that the clay is suitable for the size of this clay is suitable to be used to fulfill the rooms near the reactor. And here are several photos how it was made. So here we can see here was located clay material, and using pressure it was moved to the part of the building where it was needed. And another picture how it was made. There's several thousand tons of the clay was used. Another example is conservation of the storage basins in the Siberian chemical plant. It was used from 1960s or 70s, and no, there were not used. The special barrier materials were not used in this case. There was just a small protective layer, and it has had some sand or something like it, and just usual natural soil, and after several decades of the work of these basins, where radioactive wastes were put in, the decision was made to close it, to stop this work, and for this purpose was used several several type of materials, and they were made several screens that were covered the pump that contained a lot of radionuclides inside. So the water was moved out, and the pulp was covered with several layers of clay, of soil, and stones, and so on. In case if we want to make a barrier materials around existing basin or facility, sometimes we can just use clay as in granules, and so just make a covering screen and so on. But sometimes if we have leakages downstairs in our deposit, it is needed to make special rather deep barriers, and it is possible to make them by two techniques, like water wall in soil technology, when you excavate your soil and put some metallic construction here, and then you fulfill it with your material. It can be concrete. It's not very federal, but sometimes it was used, or with clay materials, and you make just like a wall around your facility, around your deposit. The other rather fresh technique, it is known as jet grouting technology. In case if you can make a wall and soil technology in the depth up to 6 meters or something like it, the jet grouting technology can be used in the depth up to 60 or even 100 meters, much deeper. So you under big pressure, you make a borehole, then you under pressure you spring the special solution that contains clay or some another material. Sometimes it was liquid glass, something like it. You spread it under big pressure. It is mixed with the soil that is located in this place, and you can make very deep, several deep boreholes, and just like you make a wall, prepare a wall made by several boreholes. It's very deep, and it's rather easy to applicate. Of course, you need special technique, but the advantage of this method is that you use a much less quantity of material, because you have prepare a mixture with the raw soil that is located in this place, and you can make a barrier in a very big depth that is not available by any other techniques. And using the jet grouting technique, the conservation of another storage basin was performed. Here's the example of making the jet grouting of the wall by jet grouting technique, and here's the results of the computer modeling of the uranium spreading in 400 years in case of if we will not make any barriers, if we will make 1 meter vertical barrier, that is possible to make like by the technique of wall and soil technology, or if we have a deeper here's for 3 meters, but I think that in this case they were made in much deeper. So you can see then deeper you make the boreholes, the deeper you have barrier, the less leakages you have. And it is for 400 years and for 1000 years. So you can see a big difference here. You can see leakages if you will make for 1 meter vertical barrier. If you will make a barrier up to the groundwater level, you see the leakages are much smaller. And the same is for another barriers. Here were made, I'm not sure that here was made, the technique was made with the liquid glass, and here it was made with clays and liquid glass. And you also can see that the leakage, that when we create our engineering buffer, leakages, we will not find any leakages in the long term. So thank you for attention. We have 5 minutes for questions if you have.
Thank you. Can you say again, where is this place where the plutonium get very far away in
Nevada
USA?
test site.
Where?
Nevada test site.
Nevada, okay. It was there something like a radioactive waste disposal? or
It was not a disposal, it was the place where radioactive bombs were tasted first level, yes.
Okay.
And I think there was a small disposal.
Okay, thank you.
Questions?
You can always contact with me
Yep.
by the email. Thank you.
Okay. Thank you again. Андрей, добрый день. Так, Андрей, вас пока почему-то не слышно. Хотя у вас микрофон включен, но звук не идет. У вас на наушниках нету переключателя случайно? Вот пока даже не шевелится у вас вот этот значочек микрофона. Может быть, там, где звук, стрелочка вот есть маленькая, выбрать микрофон. Вот пока ни один, видимо, не работает.
Ага, так, стоп. А
О,
тут
вот так, пошел звук. Отлично.
оригинально.
Все, теперь слышно.
Нет, самое смешное, что я включил сейчас микрофон на наушниках,
Ага.
а наушники выключил.
А,
То есть я как раз вот я пробовал все, звука не было. Теперь вижу, звук пошел. А выбрано меню у меня, микрофон встроенный на наушники. Но думаю, раз на наушники, надо сразу их одеть. Берусь одевать и вижу, что он у меня выключен вообще. Но
отлично.
тем не менее звук есть, значит, слава богу, это хорошо.
Да.
Так, тогда знаете что, мне
Попробуйте, запустите на всякий случай, проверить сейчас, что...
да-да-да, поскольку я, "Зумом" практически не пользуюсь,
Мгм.
преимущественно, чё у нас там было, "Вебексом" и иногда "Тимсом".
Мгм.
Сейчас попробуем, запустить. Так, что-нибудь. Ну, давайте посмотрим. Ага, ну вот, к примеру, вот так, а это у меня какой экран? Оригинально. А я не вижу тех экранов, которые я могу. Ну, давайте пусть так. Сейчас, знаете, 1 секунд. Я сначала проверю, на каком экране он у меня будет показывать. А то у меня получается, экран на ноутбуке и 2
Мгм.
экрана этих. И когда я запускаю показ слайдов, я заранее не знаю, на каком из них он будет показывать. Поэтому может быть не то. Сейчас, секундочку. Так. Ага. Он запускает на том, который мне все загородил. Ладно, значит, мне надо шарить тогда. А так, как же я тогда буду видеть зум? Стоп. Сделаем тогда не по-русски. Ну, поменяем их местами. Сейчас, 1 секунд. Сейчас я тогда придумаю. Тогда это я брошу сюда. Это я двину сюда. Так, еще раз пробуем. А если... Ага, так, все это здесь. Замечательно. Тогда это... Значит, сейчас вы видите
Мгм.
мелких слайдов. И если я
Да,
запускаю их в режим демонстрации, вы видите один слайд
все
нормальный,
отлично,
в режиме
да.
можно работать.
Мгм.
Ну, все замечательно. Тогда, значит,
Мгм.
у нас где-то примерно чуть меньше, чуть меньше часа, 50
Да,
минут
да.
времени. Я последний раз сейчас пробегусь по слайдам. Или на всякий... А нет, ну...
Попробуйте переключить слайд, что он переключается, то бывает иногда. Да, все, анимация видна, переключается. Все отлично.
Все, хорошо. Все, спасибо вам большое за проверку.
Да,
Что,
вам
как у вас
тогда через 50
от
минут
обеда?
примерно
Да,
встречаемся вновь.
да. Я по той же ссылке захожу и делаю все то же самое.
Можно,
Или,
можно остаться, можете пока видео и
да,
звук
я просто
выключить, да
сейчас
и все.
выключу микрофон и отключу видео. Вот, и
Да, и
просто...
демонстрацию тоже пока можно выключить.
Ой, а я
Потом уже. Вот, все.
отключилась, да?
Да.
Все, спасибо большое.
Все, на
До
связи.
встречи.
Так, Андрей, в целом мы готовы.
Так, меня слышно?
Да, слышно, но пока не видно почему-то.
Вот я этого тоже не могу понять. Я включил.
Да, значок камеры активный, но черное изображение.
Так, вот тебе и здрасте. В прошлый раз у меня Zoom запрашивал разрешение на пользование камерой, и я это разрешение давал. Сейчас он почему-то у меня разрешение не спросил, но его,
Мгм.
может быть, из-за этого. Но если... Да, сейчас я на секундочку попробую расшарить экран,
Да.
видите, потому что если не видно только мое лицо, то это не самое страшное. Если презентация пойдет, я думаю, это гораздо важнее. Так, сейчас давайте я попробую расшарить экран. Так, с экраном все в
Так,
порядке?
экран, да, экран виден.
Ну
Все
тогда,
отлично.
как говорится, и бог с ним, что меня не видно, конечно. Ну,
Ну,
буду чувствовать себя немножко свободнее. Значит, Андрей, перед тем, как начнем, у нас язык английский, да?
да, 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 да. Мгм.
Хорошо. Ну тогда не знаю, вы скажете, я потом представлюсь или как?
Да, 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 да. So, dear colleagues, we continue with the next lectures from Andrei Guskov, who is expert of International Atomic Energy Agency. So, Andrei, please, the floor is yours.
Thank you, Andrei. Thank you for introduction. You see that my name is the same. I'm also Andrei. So I'm working for the IAEA from 2015 as a waste safety specialist. And before joining the IAEA, I was working in Russia in the technical support organization for the Russian regulatory body, so-called SECNRS, and before that at Moscow Radon. So I have some practical experience both in, how to say, operating of waste management facilities and also related to regulation. And almost most of, how to say, my working career, I'm dealing with safety aspects of not only waste management, radioactive material management, I would say like this. So today I have two presentations, one after one. The first one is related to predisposal, while the second will be focused on disposal. They are not parallel, they are not absolutely equal, because the first presentation I will introduce a little bit more about the overall system of IA safety standards, maybe a little bit more, and less on more detailed aspects. While talking about disposal, so the accents or focus will be in slightly different area, but also very close to this. So why it is important to talk about safety? Because for sure it's very important to have developed technologies, to have enough resources, and quite often we think that if we do our best, it's really the best. But not only from the waste management safety point of view, but just from your ordinary life, you see that if you do not ask yourself from time to time, what I'm doing this for, what is the purpose, what are the objectives, quite often we get either wrong results or not the results we would like to get. That's why, so all these aspects related to waste management, from our point of view, always should be under the umbrella of safety. And that's why in our community, quite often we use the wording safety first. So in this presentation, as I told, I will have a few slides about IA safety standards on predisposal. And then I will stop, in fact, on one, I would say, key safety standards related to predisposal, and a very brief summary. So first, about the system. Why IAEA is dealing with this? It's very simple, because from 2057, when the IAEA was established, it was fixed in the status that it's one of the IAEA functions to establish or adopt, in consultation and where appropriate in collaboration with the competent organs of the United Nations and with the specialized agencies concerned, standards of safety for protection of health and minimization of danger to life and property, including such standards for labor conditions, and to provide for the application of these standards. So, what are advantages and disadvantages of IE safety standards? Because there are not in terms that really more than we need, but there are significant amount of countries as a member states of the United Nations and of the IEA, and they are on absolutely different level of science, technology, nuclear development, and so on. And from this point of view, quite often it's very difficult really to establish safety standards that should be equally useful and helpful for each country. Because the main, I would say, philosophy of the IAEA, including establishment of safety standards, is that we are not looking for the truth. The IAEA is looking for consensus. So that's why quite often people do not like IAEA safety standards, saying that they are quite often practically not useless, but not very, very helpful. And from one point of view, it's true, because as I told, we try to find consensus between all, how to say, member states, and it brings, how to say, difficult additional bindings for our activity. But what we always repeat to the all member states, that IAEA safety standards are binding for the IAEA's own activity. So they are not binding for the member states. They might be adopted by them. And of course, they should be binding and implemented when we are talking about any official activity between the member states and the IAEA, like integrated regulatory review service, technical cooperation projects, different projects, and so on. And here you see the links where you can find all current acting safety standards, when you can look for any standards related to some specific topics, and even find existing e-learning materials in different areas of safety for radioactive waste management. So talking about the system of safety standards, it's standard hierarchy like pyramid, and it's very typical for many countries because it's found applicable in real life. So, and if talking about IAEA safety standards, on the very top we have fundamental safety principles, and below these principles we have requirements, legal, technical, and procedural safety imperatives. And the next level of IAEA safety standards, it's guidance, maybe not on the best practice. I personally do not like the term best practice, because what the best for one country might be not applicable for another one. But on the real, how to say, good practice and acceptable practice, how given recommendations how to meet the requirements established in the safety requirements. So it's another, I would say, form of representation of the IAEA safety standards, where you see these safety fundamentals in the center, and the safety requirements around it, and much more recommendations how to fulfill these requirements on safety. So, and the key document on the overall system of IAEA safety standards is Safety Fundamentals, as it was already mentioned. And the main objective of, as fixed in the safety fundamentals, is the objective of radioactive waste management is to deal with the radioactive waste in a manner that protects human health and the environment now and in the future without imposing undue burdens to future generations. So it looks simple enough. It looks like simple to understand, but practice show that the different countries understand this principle, might understand this principle in a different manner. So if you'll have time for discussion, just remind me, and I could, I would say, talk about different point of view in different countries of this key principle of safety fundamentals. So, and in addition to this objective, it also includes or states 10 safety principles covering responsibility for safety, a role of government, leadership and management, justification of facilities and activities, optimization of protection, a limitation of risk to individuals, protections of present and future generations, prevention of incidents, emergency preparedness and response, protective actions to reduce existing or unregulated radiation risks. And coming to the next level of IA safety standards, we are going to safety requirements. And as you could see on the slide, there are two types of safety requirements. The first and maybe the main is general safety requirement, and there are 7 general safety requirements. I guess I do not need to read all of them. I only would like to highlight, and maybe I will repeat it several times during both my presentations, that all these 7 general safety requirements are applicable to any kind of activities and facilities related to radioactive waste management. So it doesn't matter if we are talking about predisposal or if we are talking about disposal. We cannot take only one from these 7 and say this is our document and we can don't care about others. No, all these 7 general safety requirements are equally important for any kind of activities and facilities related to waste management. And the second level of requirements are really focused on specific kinds of facilities and activities. You see, starting from the site evaluation for nuclear installations, for power plants, and in our case, not now, but on the next presentation, we'll talk about SSR5, focused on safety for radioactive waste disposal facilities. But during these presentations, we are more dealing with not specific, but general safety requirement, a general safety requirement part 5, predisposal management of radioactive waste. And again, keeping in mind that all 7 general safety requirements are, how to say, very important for any kinds of facilities and activities. When talking about predisposal, we can indicate a few safety standards really focused much more specifically on predisposal of waste management. And on this slide, you see some of these safety requirements and safety guides. Again, I'm not going to talk too much about each of these documents right now, just to show you, how to say, what are most important here. And maybe just mention that when talking about predisposal, some of these safety standards now are under revision, and in particular, the main one, General Safety Requirement Part 5, Predisposal Management of Radioactive Waste. How to say, the revision of this document is just initiated, and the first consultancy took place just in the very beginning of this month. So, and in parallel with this document, 2 also very important safety guides are initiated for revision. It's GSG3 safety case and safety assessment for predisposal management of radioactive waste, and old enough document old enough safety guide on storage of radioactive waste. They three of them are initiated for revision in parallel and are going to be revised in 2028, as far as I remember. So during this presentation, I'm not going to stop too much on this slide on waste classification. This is a picture taken from General Safety Guide 1 on classification of radioactive waste. And now I'm, sharing this slide only with the one purpose. So when looking at the slide, without any digits, without any numbers, you see not the bottom line, but just above the bottom, it's also close to horizontal line with exempt waste. And everything that is above is subject of presentation, this presentation and the next one. This was the only reason why I showed you this slide, this picture, this graph, and I'm not going to stop on each class of radioactive waste, just to say that exempt waste meet the criteria for clearance, exemption, or exclusion from regulatory control for radiation protection purposes. So everything that is above this level, should be subject for waste management. And not reading the next, it will be maybe more important when we will talk about disposal, but not now. And just also maybe mention right now that even when we can classify some kind of waste as according to one of these classes, it does mean that this waste or waste package might be safely disposed in any specified disposal facility. It's specific, it's something related to waste acceptance criteria, and we very briefly will touch these aspects during the next presentation, not in this one. So, and as I told during this presentation, I'm going to focus on general safety requirement part 5. And its objective is to establish the requirements that must be satisfied in the predisposal management of radioactive waste, and to set out the objectives, criteria, and requirements that apply to all stages of predisposal management facilities. Because yes, when talking about waste management, we usually consider predisposal and disposal. Predisposal is subdivided in processing, storage, transport. Processing accordingly is subdivided in pretreatment, treatment, conditioning, and so on and so on. But if talking about any kind of facility, it also is going through different stages. And this safety requirement is going to cover as well as all aspects of waste management related to predisposal, and also all stages of facility development. So, and the scope of this safety requirement includes predisposal management of all types of radioactive waste. In other words, everything that is above exempt waste, and also predisposal management from generation up to disposal, including processing, storage, and transport. So if looking at the content of this safety requirement, you see that it might be subdivided into 5 main areas, starting with introduction, also related to protection of human health and environment, responsibilities of government, regulatory bodies, operators, and so on. Steps in the predisposal management of radioactive waste, addressing waste minimization, characterization and classification, and so on, and development and operation of radioactive waste management facilities and activities. Almost a half of these requirements are related to development and operation of waste management facilities and activities. So, talking about very general aspects of waste management, what should be done? So this document have few statements related to responsibilities associated with predisposal waste management, which includes clear allocation of responsibilities throughout the entire process of waste management, assurance and confidence within the regulatory and the legal framework, and continuity of responsibility over time and location. So, why it is important? So, even looking not too far from today, I'm talking about looking back to just a few decades, you see that the borders between the countries, some of the countries were changed, so restructured. So, and from this point of view, unfortunately, sometimes the control over radioactive waste might be lost, and that's why it's very important to establish such kind of continuity of responsibility over time. From the other side, when looking for the normal situation, when nothing related to policy and I would say more general aspects is changed, when the situation is more or less stable, again, when looking at just waste that are very fresh, just are produced or generated. So it means that in most of the cases, it's traveling from one facility, from facility generator to maybe a waste management facility for treatment and conditioning, then maybe for some storage, and finally for disposal. And between these different facilities, it's also transportation. So it involves a few different entities, and it's very important to establish for each of this moment, for each of this organization involved in the management of radioactive waste, who is what organization is responsible for what. So it's very important how to really to build, to control, and to assure safety for waste management. Coming to a legal, regulatory, and policy framework, there are three requirements related to a legal and regulatory framework for waste management, a national policy and strategy on radioactive waste management, and responsibilities of the regulatory body. So separately, it's a requirement for operating organizations, and also three more requirements related to integrated approach to safety, including requirements in respect of security measures, interdependencies between different, how to say, stages of waste management, and overall management system related to waste management. A little bit closer to each of these requirements. So requirement one on legal and regulatory framework states that the government shall provide for an appropriate national legal and regulatory framework within which radioactive waste management activities can be planned and safely carried out. This shall include the clear and unequivocal allocation of responsibilities, the securing of financial and other resources, and the provision of interdependent regulatory functions. Protection shall also be provided beyond national borders as appropriate and necessary for neighboring states that might be affected. So, when talking about second requirement, it relates to the national policy and strategy on radioactive waste management. So it's important to assure the effective management and control of radioactive waste. And the government shall ensure that a national policy and strategy for radioactive waste management are established. The policy and strategy shall be appropriate for the nature of and the amount of radioactive waste in the state, shall indicate the regulatory control required, and shall consider relevant social factors. The policy and strategy shall be compatible with the fundamental safety principles and with the international instruments, conventions, and codes that have been ratified by the state. The national policy and strategy shall form the basis for decision-making with respect to management of radioactive waste. So quite often when talking with the waste management specialist, they used to say, so it's out of our business, it's too far and very high from us. But the life show that if such important aspects are not solved, if the policy and strategy are not in place, are not developed in time and how to say really implemented, any activity related to implementation of different decision related to waste management, either it is a development of a storage facility or disposal facility, will face with many significant problems and most probably will fail. So in principle, policy and strategy of radioactive waste management, it's really how to say very important thing. And I guess recognition of this importance, I suppose I can't say that it's 100% for sure. So, but I guess it was one of the key reasons why, at least for European Union, the independent review of national program for waste management is required. And in this field, I established so-called Artemis missions. And I personally took part in several of these missions, and from practice, really was able to feel how important the national policy and strategy for waste management is, and I'd say how helpful it might be for implementation of any decisions, and I'd say why all these aspects are talked about, why it is required in this safety requirement. So in principle, I have a few more slides specifically related to national policy and strategy, and if we'll have some time at the end of this presentation, we can talk a little bit more about policy and strategy. So this is, I would say, more obvious responsibilities of the regulatory body, and again, it's almost in place in many countries. And again, coming back to the different kind of IAEA emissions, I could just remind about IRRS mission, which is really focused on regulatory aspects in the country. So the regulatory body shall establish the requirements for the development of radioactive waste management facilities and activities, and shall set out procedures for meeting the requirements for the various stages of licensing process. The regulatory body shall review and assess the safety case and the impact assessment for radioactive waste management facilities and activities as prepared by the operator, both prior to authorization and periodically during operation. The regulatory body shall provide for the issuing, amending, suspension, and revoking of licenses, subject to any necessary conditions. The regulatory body shall carry out activities to verify that the operator meets these conditions. Enforcement actions shall be taken as necessary by the regulatory body in the event of deviations from or non-compliance with requirements and conditions. So, but of course, the key responsible entity when we are talking about safety of waste management is the operating organization. That's why requirement 4 states that the operator shall be responsible for the safety of predisposal radioactive waste management facilities or activities. The operator shall carry out safety assessments and shall develop a safety case and shall ensure that the necessary activities for siting, design, construction, commissioning, operation, shutdown, and decommissioning are carried out in compliance with legal and regulatory requirements. So predisposal management may involve, as I already told, transfer of radioactive waste from one operator to another. Waste is often sent from a producer to a central facility. Storage periods can be long and extend over. That's why for all these cases, the responsibilities of different operators should be clearly established in the country. So coming back to responsibilities of the operator. The operator shall be responsible for the safety of predisposal radioactive waste management facilities or activities. Okay, sorry. In fact, it's the same. The only point is these bullets under this key statement, and I only mention one from this. I'm not going to read everything, just to attract your attention to the derivation of operational limits, conditions, and controls, including waste acceptance criteria, to assist with ensuring that the predisposal radioactive waste management facility is operated in accordance with the safety case. So just, I would say, focusing on two aspects, safety case and safety assessment, and waste acceptance criteria as part of limits, controls, and conditions. So this is obligation of the operating organization. This is important to fix it. So it also includes a lot of other responsibilities related to training of staff, establishment of and implementation of management system, maintenance of records, and establishment and the maintenance of a mechanism to provide and ensure adequate financial resources. So what is also important, as soon as we are talking about radioactive waste, and they might be absolutely different from very, very low level waste, very short-lived waste that are not, in fact, are hazardous for the human. But again, the level of this potential hazard differs related to the properties of the waste. And in some cases, security measures are not simply important, but over-important. And that's why it's really very important to build some kind of interface between safety and security, and at least not to forget about security measures. So measures shall be implemented to ensure an integrated approach to safety and security in the predisposal management of radioactive waste. Safety and security to be approached in an integrated manner with the level of security commensurate with the level of radiological hazard. So, and as I already mentioned, I guess 2 times, that there are some interdependencies among the steps of predisposal management of radioactive waste and impact of anticipated disposal option. And they should be addressed and should be taken appropriately taken into account at different steps of predisposal waste management. And that's also, it's important to consider established acceptance criteria for disposal of waste, or the criteria that are anticipated for most probable disposal options. But again, looking through different countries, in fact, we do not have too much licensed disposal facilities. And in practice, it's much more important activities and facilities related to predisposal waste management. And until disposal facility exists, until it is licensed, it doesn't have waste acceptance criteria for disposal at this particular disposal facility. So, but in any case, before this facility is established and commissioned, the waste should be managed somehow. And moreover, it's important to keep in mind the potential disposal options. But what is more important, how say, to provide safety for predisposal operations, for example, for storage. And from this point of view, storage facility it should also have waste acceptance criteria for storage, so which really helps to provide safety during storage period. Of course, if we do not take into account, if we do not address interdependencies and the next step in the waste management, it might require reconditioning, how to say, additional resources for this and so on and so on. But it's another, how to say, story. If talking about safety, if considering each predisposal waste management step from safety point of view, the first objective is to provide safety at each of these steps. So, and from this point of view, waste acceptance criteria might be also, not might be, should also be derived for each of predisposal waste management facility and activity. So, I'm not going to go too deep into management systems, because I can't say that it's the whole world, but it's really so integrating. It covers so many aspects related not only specifically to radioactive waste, but to any activities which is going on waste management facility, even if it isn't directly connected to waste management. So all these aspects, both of waste management and of any activities on this waste management facility, should be covered under the integrated, how to say, management system. And this management system should be established really to guarantee or to ensure that everything is done properly and all the requirements, all the recommendations are in place, and it provides safety for waste management. So, requirement 8 states that radioactive waste, all radioactive waste shall be identified and controlled. Radioactive waste origin shall be kept to the minimum practicable. So, again, not going deeper into this, it's one of the principles implemented in most of the countries, waste minimization. So, if it's possible not to use radioactive materials or not to generate radioactive waste, it's a preferable option. But as soon as radioactive waste appears, if they are generated, so we should know as much as possible about this waste, really to provide safety for waste management, both for the staff and for public. And from this point of view, characterization and classification of radioactive waste is required. At various steps in the predisposal management of radioactive waste, the radioactive waste shall be characterized and classified in accordance with the requirements established or approved by the regulatory body. And how to this again, it's one of the schemes recommended by the IAEA, but it does mean that all the countries should follow exactly how to say this scheme. Some of the countries might not have high-level waste. Some of the countries might not consider intermediate depth disposal facility and only near surface disposal facility and deep geological disposal facility. So they might exclude intermediate level waste from consideration. Some other countries are going deeper, and they also introduce even tarification, addressing different potential options for processing of different waste streams, and use more waste classes than it is presented here. This is how it's the philosophy of radioactive waste classification, and this is one of the reasons why you do not see any numbers, any levels, but just the idea to remind every time people and organization involved into the waste management that the final step of waste management is disposal, and at each step of waste management, of predisposal waste management, they, how to say, have not to forget about the final step, about disposal. So in fact, I told how to say almost the same, that it's just an idea, it's a philosophy, and in different countries radioactive waste are classified by the origin, physical state, activity concentration, half-life, taking into account disposal routes, or try to merge and try to implement as much as possible all these, how to say, features altogether, it's up to the country. So what is more appropriate? So it's just an idea. But in any case, any country should introduce their own waste classification scheme addressing their current situation. At first, the waste they do have, the resources they have and can spend for providing safety for waste management and so on. So after waste are classified, we are coming to the next step and talking about predisposal. So we are moving to processing of radioactive waste. Radioactive material for which no further use is foreseen and which characteristics that make it unsuitable for authorized discharge, authorized use or clearance from regulatory control shall be processed as radioactive waste. The processing of radioactive waste shall be based on appropriate consideration of the characteristics of the waste and on the demands imposed by the different steps in the management: pretreatment, treatment, conditioning, transport, storage, and disposal. Waste packages shall be designed and produced so that the radioactive material is appropriately contained during both normal operations and accident conditions that could occur in the handling, storage, transport, and disposal of waste. So waste shall be stored in such a manner that it can be inspected, monitored, retrieved, and preserved in a condition suitable for its subsequent management. Due account shall be taken of the expected period of storage. To the extent possible, passive safety features shall be applied. For long-term storage, in particular, measures shall be taken to prevent the degradation of waste containment. So I just will stop at one moment, which from my point of view, it is really very important. Unfortunately, in many countries or some old historical or from old practice disposal facilities, which don't meet current safety requirements for disposal, were just renamed as storage facility. And from this statement, you see that it is not correct. So in principle, I can't imagine how such storage facility in principle might be licensed as storage facility if they were not designed, constructed as storage, if they didn't envisage inspections, monitored of waste packages, retrieval technology and resources, and so on and so on. So I just would like to highlight that if something doesn't fit with the requirement for disposal, please do not rename it as a storage facility, because storage facility also have their own very strict safety requirements. And it's incorrect just to rename any facility from old type disposal to the storage one. In fact, just small remark, which from my point of view is really important in practice. So a very interesting and very important requirement related to waste acceptance criteria, which in fact was already mentioned several times. And to address this topic in more detail, we'll need a few more presentations addressing different aspects. So that's why here just briefly. But as I promised, if you have more specific questions related to waste acceptance criteria after end of this presentation, or even after the end of the next presentation, you're welcome. I will try to tell a little bit more about waste acceptance criteria. So, but here, if we are looking at General Safety Requirement Part 5 on predisposal waste management, we see how it is stated here. Waste packages and unpacked waste that are accepted for process and storage and disposal shall conform to criteria that are consistent with the safety case. So again, we are mentioning safety case, but at this moment, I'm not going to stop on this and to explain what does it mean if you do not understand what we are talking about. It's also a separate topic, and we will touch it a little bit more in the next presentation on disposal. And if you will need, I can stop on this as much as you need, because it's in fact safety assessment and safety case. It's the key subject of my activity last decades. So preparation of the safety case and supporting safety assessment. So it was already mentioned that the key responsible organization, key organization responsible for this is the operatory body. That's why it is not repeated but focused here, that the operator shall prepare safety case and supporting safety assessment. And the safety case, a step-by-step development, or in the event of the modification of the facility activity, the safety case and supporting safety assessment shall be reviewed and updated as necessary. When we are talking about reviewed and updated, so updates of the safety assessment and safety case, it's an obligation of the regulatory body, but in most of the countries, it's also required to have a regulatory review if the safety assessment and safety case is updated. So-called periodical safety review quite often is prescribed in the national regulation. Coming to the scope of the safety case and supporting safety assessment. It should include a description of how all the safety aspects of the site, design, operation, shutdown and decommission of the facility, and the managerial controls satisfy the regulatory requirements. The safety case and supporting safety assessment shall demonstrate the level of protection provided and shall provide assurance to the regulatory body that safety requirements will be met. So at first that they are met now and will be met in future, because the license usually is issued for the future time. So, and of course, as soon as safety assessment is performed and safety case is developed, it should be documented. And it should be documented in a level of detail and quality sufficient to demonstrate safety, to support the decision at each stage, to allow for independent review and approval of the safety case and safety assessment. The documentation shall be clearly written and shall include arguments justifying the approaches taken at the safety case on the basis of information that is traceable. So it might be not clear what does it mean enough, clear enough, and so on and so on. That's why it's very important that in every country the regulatory body could clearly identify what does it mean for them. So because if the operating organization clearly understand what the regulatory body is requiring or expected from them to be demonstrated, it's much easier really to develop such a demonstration. If such criteria are not established in the country, so it means that it will be much more gray area, much more potential misunderstanding between the operating organization and the regulatory body. And it's always important to keep in mind that there are not two fighters on the ring, like operators and regulators. In fact, there are two sides of one entity. They all are performing the same task for the country. So the operating organization really try to manage with the waste, and the regulatory body is really trying to assure that this management is safe. But both of them are in fact are working on the same objective, but not opposite objectives. And that's why it's important not to fight, but really to establish a good coordination. And as I told, if regulatory body establish, how to say, enough safety requirements and regulation, clearly explain what does that mean safe, how a safety assessment should be performed, how safety case should be developed, how this should be documented for application to the regulatory body. The more is done by the regulator, the easier it will be implemented by the operator, and the easier it will be to review provided materials, to review this application, and to make the final decision. It's about periodic safety review. And that's, again, I already mentioned, the operator shall carry out periodic safety reviews and shall implement any safety upgrades required by the regulatory body following this review. And the results of periodic safety review shall be reflected in the updated versions of the safety case for the facility. In many countries, the maximum period before periodical review is 10 years, but it depends. It's not the one digit for all the countries. And moreover, quite often, if any changes took place in the regulation, if something happened not on this specific facility, but on similar facility, maybe even abroad, some additional review might be required. But again, it would be much better if such conditions, when periodic safety review or additional safety review of safety assessment and safety case is to be performed when it is, how to say, prescribed by the national regulation. As I already told, so it's one thing when we are talking about waste management and moving from the waste from waste generator to waste management organization and final to disposal. And another story is when we are talking about some specific waste management facility, which usually starts from siting and design. And for this, we have requirement 17. Pre-disposal radioactive waste management facilities should be located or sited and designed so as to ensure safety for the expected operating lifetime under both normal and possible accident conditions, and for their decommissioning. And it's a very good remark to come back to the topic which I didn't discuss, just indicated that it is important, about national policy and strategy. If there is no clear identification in the country, especially when disposal facility doesn't exist yet, so if it isn't indicated in the national plan when disposal facility will be constructed and operated, it's impossible to fix how long storage facility will exist. So, and in this, it means that we do not know operating lifetime for storage facility, and how in this case it will be possible to license such facility if we do not know for how long, for how many years this facility should be designed, constructed, and what we should, how to control every time should we focus on during the safety assessment and safety case. So that's why all these things are very important, and that's why I mentioned that the development of the national policy and strategy for waste management is one of the key, how to say, element of safety in any country. And again, address your attention, just for those who maybe do not know, even when we just start the lifetime, the facility lifetime, when we just establish this facility, when we just are going to get the license for construction of this facility, even at this moment, we already start thinking about decommissioning of this facility, because any predisposal waste management facility, sooner or later, should be decommissioned. And during decommissioning of predisposal waste management facility, some amount of radioactive waste from decommissioning might arise. I would say they will arise, but how to say, to be more safe, I would say might arise. And how to say, what to do with this waste from decommissioning, how to process them, where to store, where to dispose, it's again should be somehow indicated in the national policy and strategy. And it's very important, do not forget about it. So, as I told, we should start thinking about decommissioning from the very beginning, even when facility is designed, because again, now there are several techniques for facility design that really may make it easier to dismantle the facility during decommissioning, and that may, how to say, produce less radioactive waste from decommissioning. So these aspects might be addressed even during design of a pre-disposal waste management facility. But as soon as it is sited, so located and designed, the next steps are construction and commissioning. These facilities shall be constructed in accordance with the design as described in the safety case and approved by the regulatory body. Commissioning of the facility shall be carried out to verify that the equipment, structures, systems, and components and the facility as a whole perform as planned. A pre-disposal radioactive waste management facility shall be operated in accordance with the national regulations and with the conditions imposed by the regulatory body. Operation shall be based on documented procedures. Due consideration shall be given to maintenance of the facility to ensure its safe performance. Emergency preparedness and response plans, if developed by the operator, are subject to the approval of the regulatory body. And again, it's not right here, but you can easily find IA safety standards specifically focused on emergency preparedness and response to be addressed in these plans that are briefly mentioned in the requirement we discussed. So, the next requirement is related to shutdown and decommissioning of facilities. The operator shall develop in the design stage, as I mentioned, an initial plan for the shutdown and decommissioning of the pre-disposal radioactive waste management facilities and shall periodically update it throughout the operational period. The decommissioning of the facility shall be carried out on the basis of the final decommissioning plan as approved by the regulatory body. And in addition, assurance shall be provided that sufficient funds will be available to carry out shutdown and decommissioning. And if in your specific case or in case of a specific facility, there are some subject for accounting and control, it also should be in place. For facilities subject to agreement on nuclear material accounting and the design and operation of pre-disposal radioactive waste management facilities, the system of accounting for and control of nuclear material shall be implemented in such a way so as not to compromise the safety of the facility. And as always, it's one of the tricky situation how to address existing requirements to the facilities that were designed, constructed, and operated in the past. So, and according to GSR Part 5, the safety at existing facilities shall be reviewed to verify compliance with the requirements. Safety-related upgrades shall be made by the operator in line with the national policies and as required by the regulatory body. So one of the advantages of pre-disposal waste management facilities in comparison to disposal one, because this facility most of the time is under operation, under the control, some changes might be implemented really to be in compliance even with updated safety requirements. So that's all related to GSR Part 5, pre-disposal management of radioactive waste. We just talked about this, and maybe just one or two slides about two more safety standards from this picture about safety assessment for facilities and activities, and the safety case and safety assessment for the pre-disposal management of radioactive waste. So, and again, as I already mentioned before, you see that these safety standards now are under revision. That's why, in fact, currently they are actual, and you could and you should use them as they are. But these are, you see just indication, so-called the numbers of the draft, so under which this new updated revised version will be developed in the nearest future. So we talked talking about this, I mentioned safety assessment for facilities and activities and the safety guide GSG3. GSRPAT 4 was reviewed not long ago. She is actual and not going to be reviewed, but as I mentioned, GSG3 now, how to say, a revision of this document is initiated. But in addition to the safety standards, I would like to show, or maybe even to recommend you, as soon as you will be dealing with a safety assessment and safety case, two more so-called informative publications, in particular tech docs. They're here. One is a methodology for safety assessment applied to predisposal waste management. It was SADRAM's project from 2004 to 2010. In fact, it was maybe the starting point for developing this GSG3. And another tech doc is another project, so-called CRAFT, the international project on complementary safety reports that took place a little bit later. So, and the first mentioned tech docs is really about safety assessment methodology for predisposal waste management. Again, we do not have time, and I'm not going to stop on this methodology. This is just to inform you that you can find this methodology in this tech doc, how to perform safety assessment for predisposal of waste management. And as I told, this is about safety assessment. While another mentioned document is about more related to safety case, and in fact it provides detailed examples of application of the GSG3 safety case and safety assessment for predisposal management of radioactive waste, for development of the safety case and performing safety assessment for operation of centralized storage facility, and another example for planning for retrieval of radioactive waste from old disposal facility. So just the last slide as a summary. So safety requirements apply to all steps of waste management up to disposal. Apply to all types of radioactive waste and facilities where radioactive waste is generated, treated, and stored. Important to consider interdependencies and compatibility between all steps of predisposal waste management, including disposal. Safety to be demonstrated in a safety case reviewed and approved by the regulatory body for all stages of predisposal waste management facility lifetime in a periodical manner. Existing facilities to be reviewed for compliance with the modern requirements. Development of safety requirements for predisposal of radioactive waste should be supported by development of corresponding safety guides. So if development of these recommendations by the regulatory body is in place, it's much easier in the country, I would say, to implement any waste management project. If it is storage project or processing project or any activity related to waste management. So if a regulatory body not only issue the requirements indicating what are the safety criteria and what should the operatory body follow, but also provide some guides and recommendations how to follow these requirements, it really will help a lot to operating organization to fulfill this requirement, and in general or in total to implement a waste management program in the country. So, and maybe the very last slide. So what's important to manage the waste from cradle? So in fact, only one from this triad was mentioned in this presentation when we talked about minimization of the waste, but two other important components are reuse of radioactive materials and recycle. So the primary goal of predisposal waste management is to provide safety and produce a final waste form that meets the waste acceptance criteria for disposal. So yes, it's really very important to manage waste safely before disposal, But what is also very important overall for the country, not to get the place, not to get the state or status when after predisposal waste management, some waste package or waste form was produced that is impossible to dispose safely in your country. So that's why it's always very important to keep disposal option in mind through all this predisposal waste management. So, but not only at each step of predisposal, we have to not, at first look at disposal, as I told, but also look back. And it's possible to say that each step of waste management forms at least technical requirements for the previous one. For example, so also it depends from country to country. It depends from facility to facility. But just in one country, in one place, there are some, for example, installation for incineration. This incineration plants for sure has some technical requirements. What kind of waste might be incinerated in this plant and which are not. What does it mean? That on the previous step, when radioactive waste are generated or maybe pre-treated, they probably must be sorted in a way that really to develop a waste stream that is applicable for this incineration facility or incineration plant and so on. So that's why, as it is written here, it's very important to look both forward up to disposal and also look back. So what is the origin of the waste and how it might be treated. So understanding the waste characteristics is essential to optimize waste processing and to dispose of waste safely. So that's why it's very important at each step of, I would say, waste lifetime. So when starting from the time when the waste were generated till their disposal, to control waste characteristics, because after treatment of the waste and after the conditioning, we might get the new waste form with the new characteristics. And that's why it's very important to characterize the waste at each step of predisposal waste management and definitely keep the records. So what did we have at the very beginning, how it was transformed, and what do we have finally before a disposal. And as I repeated several times, we quite often use to repeat that safety first, safety in terms of safety assessment and safety case, but safety isn't the only option for decision making when we are talking about national policy, strategy, and program for radioactive waste management. In fact, that's all that I was going to present you. So, and as I mentioned, I have more slides, and if you have more questions, I can use the slides to address your questions. But at this moment, I guess I will stop. At least I will try to stop sharing.
Thank you.
Unfortunately, still black screen and not my face.
Yeah. But maybe somebody have questions? Any questions? No, I actually have one question. When we are talking always about this safety standards and updating of them, um, what actually is the time when these safety standards are relevant? I mean, if we will look on the storages or disposals that were in the past, maybe even 30, 40 years ago, nowadays experts says that they are not really safe according to the modern standards. Yeah, and we should replace the radioactive waste in new storages, etc. So what really the time when we reconsider, I don't know, the standards and should manage the radioactive waste in a new, maybe more safe way. Is there any not regulations, but maybe from the expert point of view, these ideas about this time?
Thank you for your question. It's an easy answer and not easy answer. So the easiest one, again, at first, there is no any justified and solid numbers which I would like to share between all the countries, all the member states, and recommend to all of you. But from the practice, we used to say that safety requirements, general safety requirements and the specific safety requirements are supposed to be reviewed. It doesn't mean that they should be changed, but they should be reviewed just to see if it is any need for some changes, for some improvement. Once for 10 years. Coming to the safety guides, so it is supposed that they should be again reviewed, at least considered as a potential for review each 5 years, because they are much more practical, and the more practice the countries have, the more, how to say, knowledge and understanding we could get, and that's why it might be more efficient to revise safety guides, safety recommendations each 5 years. And if talking about not safety standard, but informative publications, like I mentioned, tech docs, but there are also technical series report and scientific series reports and so on. So the list of non-safety standards publications is, how to say, quite wide in the IA. We usually used to say that their lifetime is just 3 years. After 3 years, they might be not actual, because the practice can go forward more rapidly than it is reflected in this publication. This is, I would say, general approach, not approach, general practice from the IA. But of course, it's normal evolution scenario, I would say, in terminology of safety assessment. Chernobyl, Fukushima, any other similar events can bring a lot of, how to say, additional input. For example, after Fukushima, I would say almost all safety standards were considered as a potential for review, if some of them should be reviewed or not. For example, such very specific aspects related to safety, like very unlikely events. Previously, the IA considered that if probability of any event is less than 10 to the minus 6 power, so if this event is, how to say, very unlikely, we might to exclude this event and consequences from consideration. After Fukushima, it was another imperative that even in case if probability of any event, and moreover combination of several very unlikely events, even if probability of such events is very, very low, but consequences might be very hazardous, this should be addressed. And so, and just to check this statement, we had to go almost through all IA safety standards to see if we need to make some changes to address this better understanding. This in fact how it goes. So similar to any country, if something happened, if technology changed, if new options appeared, so some just a national policy and strategy was significantly redeveloped, not just updated, but significantly changed to another, how to say, direction. For example, it's a signal to check your safety standards in the country, and to double check if any of them should be adjusted to the current situation. That's all.
Thank you very much. So now we have a short break. Will it be okay for you if we will start in 15 minutes?
15 minutes is more than enough. Thanks a lot. So okay. It's really strange. I do not see myself in the big screen, but above the screen I see my small face. So thanks a lot for this very brief minutes. Definitely 15 minutes is it's enough. Thanks.
Okay, so we will start in 3:30. Okay.
Yes. Thank you so much.
Okay.
See you.
Okay. See you. So we are ready to continue. Микрофон пока выключен.
Sorry. So it means that I clicked it twice. Okay. Okay. So I will start, or I will continue. It's up to you as you wish.
Yep.
So as I told before, the second presentation is about disposal. But before going to safety standards on disposal, let's spend a few slides and a few minutes about terminology on disposal. What do we understand? Because the term is usually widely used, but what does it mean? So the IAEA published not only safety standards but and informative publication. From time to time, it periodically also published so-called glossaries. And the latest glossary we have now is from 2022. You see it on screen. And when you try to find a definition for disposal, again, it's not to read, but just to show you that it's the whole page explaining what does disposal mean from the IAEA point of view. Not going deep into all these things, I would highlight how the three main meaning from this page, that it's emplacement of waste in an appropriate facility without intention of retrieval. So, and here I would like to underline two things: not any facility, but appropriate facility. And usually it's supposed that if facility is appropriate or not should be decided by the regulatory body in accordance to existing national requirements and the recommendations. And the second key moment here, term here, is without intention of retrieval. It does mean that the waste cannot be technically retrieved, but at least intention is absent. So the second definition is almost the same, but slightly enlarge the term. And then it says emplacement of spent fuel or radioactive waste in an appropriate facility without intention of retrieval. And the third definition means that it's not only emplacement, but in fact the process of getting this waste, how to say, without intention of retrieval. So this is what in general is understood by the IAEA on the disposal. In principle, it brings us some more reasons to stop a little bit about spent fuel and disposal sources, but maybe we'll come to it a little bit later. So after this definition, there are already some disposal facilities in the world. They were constructed and operated many decades ago. The first, there are some existing, and so now we can say about different disposal options for radioactive waste. And special safety requirement 5, paragraph 1.10 states that a number of design options for disposal facility have been developed, and various types of disposal facilities have been constructed in many states and are in operation. These design options have different degrees of containment and isolation capabilities appropriate to the radioactive waste that they will receive. The specific aims of disposal are to contain the waste and to isolate the waste from the accessible biosphere and to reduce substantially the likelihood of and all possible consequences of inadvertent human intrusion into the waste. So, and from this point of view, we could say about some facilities constructed above the ground level, very similar to the storage one. It's well, very short-lived waste. There are also some kind of, in practice and in reality in different countries, landfills for very low-level waste. Now they are recommended for the waste, by the way, in particular for the waste from decommissioning, which usually have very low activity and not, how to say, half-life, a long time half-life. So more or less a standard near surface disposal facility for low-level waste. There are also some waste that cannot be safely disposed near surface, so below a few meters, on or below a few meters from the ground level, mostly because we cannot guarantee that we can exclude potential inadvertent human intrusion into this facility in the future. Because when we are talking about disposal, we usually consider time frames of several hundreds of years. And of course, it's very difficult to guarantee that within this period, for example, of 100 or 300 years, no inadvertent human intrusion might take place in this facility. That's why it was told about intermediate level waste that should be disposed deeper than near surface, really trying to exclude inadvertent human intrusion. And another kind of waste with very long half-life, with a very high activity concentration, that really needs much deeper isolation. And usually in this case, we are talking about a deep geological disposal facility. And just by the way, not coming in detail back to the waste classification, well, we have it on the next slide. Maybe we'll do it like this. So again, I'm coming back to this waste classification, which was already introduced last time. So, and I told that during these both presentations, we consider the waste above the exempt level line. So all that is above with the radioactive waste and it's subject of predisposal or disposal waste management. And here you see this classification introduced by the IEA as very low-level waste, low-level waste, intermediate level waste, and high-level waste. And what I would like to highlight, quite often when people from different countries translate their own national classification of radioactive waste, they use the same terminology, but they do it not in a proper way. Not because they made a mistake, but not always this difference is absolutely clear for people even involved in the waste management. In most of the countries, and just by the way, the previous classification of radioactive waste, which was in the IEA, recommended by the IEA, it was based on the activity concentration. And in reality, in many countries, when people are talking about different level of waste, they're talking about low activity level waste, intermediate activity level waste, and high activity level waste. While in fact, in this safety guide, in GSG1, in this picture, in this classification, you do not see, you will not find the term activity. It's really high level waste in terms of hazard, level of hazard. It's high hazard, level of hazard waste, intermediate hazard level waste, low hazard level waste. So it's not only the activity. That's why if in your national language, your waste class is called like intermediate activity level waste, please do not call it as ILW, because it will not be correct. Because quite often, even during general conferences, joint convention, and any other very, how to say, big international events in the IEA, people continue using that we are going to dispose intermediate level short-lived waste in near surface disposal facility. It's completely against the IAEA waste classification. If you assign some waste as intermediate level waste, it means that they cannot be safely disposed in near surface disposal facility. If they can be disposed, it doesn't matter what activity level is. If you can dispose something safely in a surface disposal facility, all this waste are low level waste, because in the IA classification, activity is not used. It's just low level, intermediate level, high level, not activity level. So just how to say, sorry that I stopped and this too much, but it's I face with this in many IA events and in different countries when we're going there for different missions, just to attract your attention to this aspect. So coming back to this glossary which I mentioned, and coming back to terminology, I already presented terms about disposal. In general, what is meant, but what is a disposal system? So in principle, this term is more related specifically to safety assessment rather than to operation and operating facility and so on. But in any case, this term exists. And in the glossary, you can find that disposal system is the same as disposal facility. So I do not know who introduced this definition, because for me, it's incorrect. So because if you will go closer, if you will switch to the definition for disposal facility, you will see that disposal facility is an engineered facility where waste is emplaced for disposal. And in many countries, it's synonymous with a repository, while in fact the IAEA recommends to use them differently, to use a disposal facility rather than a repository. So, and from this point of view, if you go from disposal facility, just again to remind you, it's an engineered facility where waste is in place for disposal. While in fact disposal system, as it is in the glossary, it's a system of properties of the site for disposal facility, design of the disposal facility, physical structures and items, procedures for control, characteristics of waste and other elements that contribute in different ways and over different time scales to fulfillment of safety functions for disposal. So in any case, even from here, from the definition from the same glossary, you see that when we are talking about the disposal system, we are considering not only engineered facilities, but also the site itself where this facility is located. And to be honest, this again, even this definition is not complete. Because when you will go again deeper to description of the disposal system, you will see that it should record all the information and knowledge about disposal system and should provide the basis on which all safety assessment is carried out. Information will be obtained that knowledge about the disposal system will evolve and mature as the project progresses, and assessment is carried out in an iterative manner. And as knowledge is developed, it should be used to determine future needs for system characterization of disposal facility, and it should contain, depending on the time of disposal facility, information of the following: the near field, including the types of waste, the origin, nature, quantities, and properties of the waste and radionuclides inventory, system engineering, in fact, what was initially called as a disposal facility, waste conditioning and packaging, disposal units, engineered barriers, caps to cover the disposal facility, drainage features, and so on. And the extent and properties of the zone disturbed by any excavation on, or construction work. All this, how they mentioned, is just so-called near field. Also, it includes so-called far field. In other words, geology, hydrogeology, hydrology, geochemistry, tectonic and seismic conditions, erosion rates that are supposed to be not interacting with the waste directly, but is like a like a transport measures, how to transport radionuclides, how to transfer radionuclides to human. And what is more important, what was completely missing from the very initial definition, the part of biosphere, in other words, climate and atmosphere, water bodies, local population, human activities, biota, soils, topography, geographical extent and location of disposal facility. In other words, how to includes also the subject for exposure. Because how we can evaluate if facility is safe or not? Just trying to evaluate what is the impact of this radioactive waste, the potential impact of radioactive waste disposal facility to human living closely to this facility or supposed to be living close to biota and so on and so on. And from the very initial definition, this part of biosphere was excluded. But it's very important to understand when we're talking about safety of any disposal facility, we should consider all these three components in a systematic manner. So, and this is, again, it's not just my wording. You can find this in Special Safety Guide 23, paragraph 4.37. So this was just an introduction. So what do we understand under disposal as a process, under disposal facility, and under disposal system as a subject, how to say, for safety? So after this, let's come back to the IEA safety standards, which in principle it's very similar that I presented you last time. So no ideas, no intention to repeat the same. So about safety fundamentals, safety requirements, and safety guides, and maybe answering the questions, the question you asked me after the first presentation. Here you see the practical values answering your question. So the need for revision of safety requirements evaluated every 10 years. The need for revision of safety guides is evaluated every 5 years. And I try really to keep the number of IEA safety standards in a manageable manners, because if there are too many safety standards, it's very difficult to at first to check consistency, not to be in a contradiction between some of them, and also to fulfill all the requirements and recommendations from the whole set of the IEA safety standards. So the same picture as it was presented, just reminding that all 7 general safety standards are applicable for any kind of facilities and activities related to waste management. But for this particular presentation, the most important safety requirement is SSR Special Safety Requirement 5, Safety of Radioactive Waste Disposal Facilities. And I also, so I didn't highlight it on the picture, but it's also very important, especially for disposal facilities, and not especially, but specifically for disposal facilities, is a general safety requirement, part 4 on safety assessment. So again, keeping in mind that all 7 general safety requirements should be applicable for any kinds of activities and facilities, including disposal. Here I tried to present maybe just some of safety standards focused or most closely related to disposal of radioactive waste. And as soon as radioactive phase classification introduced by the IAEA is based on disposal option. It is one of these safety guides. Also, there are 3 safety guides for different options for disposal of radioactive waste. So we do not have intermediate depth disposal facilities, and it was decided not to develop specifically such kind of safety guides. But we have safety guides on geological disposal, on near surface disposal, and a separate one more safety guide. It was just revised. That's why the cover is slightly different, because it's really a very fresh document, and the style of cover will be changed. So it's related to borehole disposal facilities for disused seal radioactive sources. And in addition to this, covering 3 types of disposal, it's a special safety guide 23 on safety case and safety assessment for disposal, covering all these 3 potential options. And maybe it's really time to say a few words, to come back to the waste classification, and to say a few words which I was going to say during previous presentation, but didn't do it because of the lack of the time. Okay, what I'm going to say very briefly, just a few more words. So, because it was mentioned in one of the very first slides when we talked about disposal, I told you have seen that it was written that is emplacement of radioactive waste and spent fuel. So, formally, we have 2 very special categories. We have spent fuel, which in some countries might be considered as a source, and some countries might be considered as a radioactive waste. Some countries, how say, continue using, calling this like a spent fuel. I'm talking about spent nuclear fuel from nuclear power plants, research reactors, and so on. And assign it as a radioactive waste at some stage, at some level, or maybe according to some very specific national criteria, when spent fuel might be assigned to radioactive waste. So, but in principle, spent fuel and disused sources are not radioactive waste. But quite often we are talking about disposal of spent fuel, and we are talking about disposal of disused radiation sources. So, and it might be some kind of a confusion. So, does it mean that we dispose not radioactive waste? So, it's a trick. So, for me, it's an artificial trick. So, why these terms were introduced and they are widely used in practice? Because many countries on the national level has laws prohibiting transportation or importing of radioactive waste into their countries. But from the other side, it's absolutely clear that not all the countries have resources for processing of spent nuclear fuel. Some of the countries have no resources to process disused radiation sources, and even for the purposes of repatriation of disused radiation sources or sending spent fuel for processing, this terminology is used. So until we do not call spent fuel as a waste, we can export them. It can cross the border and reach other country. But from the safety point of view, it doesn't matter how you call it. That's why all IAEA safety standards you can find in the scope. They are intended to be used to be implemented for radioactive waste management. And in principle, to be absolutely precise, if spent fuel is not officially assigned as radioactive waste, you can say it's out of our business. We don't care about IA safety standards on waste management. It's not the waste. And legally, it might be correct. But in terms of safety, to provide safety for spent fuel management, to provide safety for disused seal radiation sources management, IA used to say that, yes, our safety standards are intended for radioactive waste, but to provide safety for management of disused seal radiation sources and spent fuel, these safety standards might be applied even for spent fuel management and for management of disused seal radiation sources. So this it's slightly, I can't say that it is, maybe it's more related even to predisposal waste management, but in fact it relates to both of them. So I kept it in mind during my previous presentation, but I didn't tell this last time. That's why I'm sorry that I, how to say, reminded it and spent some time addressing these aspects. But I guess it's important to keep it in mind. So, and as it was already mentioned, the key safety standards in terms of disposal is a special safety requirement 5, a safety requirement for disposal of radioactive waste. And this requirement applies to all types of radioactive waste, you see. So radioactive waste, not spent fuel, not disused sources, and to all types of disposal facility. So it covers operational and post-closure phases of disposal facility. It's consistent with ICRP publication 7781 and 103. It doesn't address broader issues of site selection because it's a specific procedure and it depends on many aspects. And at first, from the type of disposal facility we are talking about. It doesn't address transport of waste to the disposal site, and it doesn't address radiological environmental impact. Stakeholder involvement in the disposal of radioactive waste is important and it is recognized, but it is not in the focus, and I could say it is beyond the scope of this safety standard. And in total, this publication includes 26 safety requirements, starting from planning of disposal facilities and addressing legal and organizational framework aspects, safety approach, safety design principles. It also addresses development, operation, and closure of disposal facilities, including framework for disposal, the safety case and safety assessment, not specifically because you have seen that it's a special safety guide on safety case and safety assessment for disposal, but on the level of requirement. So the key requirements related to safety case and safety assessment are stated in this document. And also steps in the development, operation and closure of disposal facility, assurance of safety, and as with predisposal, it also have some paragraphs related to existing disposal facility. So here you see 26 requirements from these documents. And in principle, after the end of my presentation, if you click on one by one, you will have one slide for each of these requirements. But I'm not going to spend the time just going through this document. This document is easily available in the internet. You can easily find it, download and read it carefully if you need it. So it's on the level of requirement. But what I'm going to do in this presentation, just come back on these safety standards related to disposal and jump to the safety guide on near surface disposal facilities for radioactive waste. Why? because at this moment we do not have even one operating deep geological disposal facility, and the most common disposal facilities which are in use, under construction, in operation, or planning by many countries are near surface disposal facilities. And that's why I decided, sorry if I'm wrong, to focus a little bit on this specific one type of disposal facilities for our presentation and for this event. So looking at the structure. So of course it's some, after introduction, it's overview of near surface disposal, then legal and organizational infrastructure, which includes the responsibilities of three key stakeholders, starting from the government, regulatory body, and operating organization. So the next chapter is related to safety approach, covering safety in the development process, containment, isolation, multiple safety function, passive safety, surveillance and control of passive safety features. And now a little bit in more detail on the aspects I just listed. A few words about legal and organizational infrastructure. Development, operation, and closure of any surface disposal facility requires the assignment of responsibilities among three types of organization: the national government, the appointed regulatory body, or in some countries it might be several bodies, and the operator facility. So independently, sometimes it's operating organization, sometimes it's an operating company contracting some several other facilities. It doesn't matter. So the organization who apply for the licensing and who get the licensing is considered as an operator in this safety standard. So the national legal and organizational framework for near surface disposal has to include the following: defining the national policy and strategy for the long-term management of radioactive waste of different types. I would say of all types of the waste that might be generated and maybe historically exist on the territory of this country. Setting clearly defined legal, technical, and financial responsibilities for organizations that are to be involved in the development, operation, and closure of near surface disposal facilities. Ensuring the adequacy and security of financial provisions, for example, by requiring the owners of the waste to establish a segregated funds. Defining the overall process for the development, siting, design, and construction, operation and closure of near surface disposal facilities, including the legal and regulatory requirements for each step, and the processes for decision making, in particular moving from one step to the next one, and involvement of interested parties if, according to the national legislation, they should to be involved into this decision making. It also might be helpful if even relations between the operator and a regulatory body might be somehow formalized in the terms of processes by the government. It really might be very helpful for implementation of disposal project. Ensuring that necessary scientific and technical experience is available to support site and facility development, operation and closure, independent regulatory review, and other national review functions. Defining legal, technical, and financial responsibilities, and, if necessary, providing for any institutional arrangements that are envisaged after closure, including monitoring arranged for security and of the disposed waste. So you definitely, I will send this presentation to the organization committee. You will have it available. So I'm not going now to go deep enough. This is just to show you what might be possible if you are interested in. So if you click on the national policy and strategy here, you will go to the end of the presentation just to see that the policy and strategy is needed. Just how to say some easy explanation why it is needed, what does it mean. some IAEA publications, not safety standards, but just publication related to policies and strategies, when you can find more information about policy and strategy. Policy and strategy, you see it here. So the links, potential links, again, not general, because it's not a safety standard, it's informational publication based on the current practice. So, but for overall understanding what does it mean, it might be useful to see the link between the policy and strategy. Why do we need the policy? Why do we need the strategy? And so on. So you can easily find it in this presentation if you will need to stop on this in more detail and go further. Now I came back to the slide we just discussed and go into the next one. The specific roles of responsibilities of regulatory body in relation to the waste management are established in the IAEA Safety Standard Series GSR Part 1, a governmental, legal, and regulatory framework for safety, and include the following: carrying out licenses, inspection, and enforcement of regulations, providing independent advice to the government in the formulation of objectives in the national policy, issuing and updating the rules, guidance, and other regulatory criteria specific to near surface disposal facility. And as it was mentioned, for more details, I would recommend to come to GSR Part 1. In developing regulations, guidance, and other regulatory criteria specific to near surface disposal facility, the regulatory body should ensure consistency with the national policy and give due regard to the objectives and criteria set out in Special Safety Requirement 5. And the regulations and guidance may include radiation protection criteria and environmental protection criteria for operational and post-closure safety, requirements for the content on the safety case for disposal facility, including the safety assessment and management system, criteria and requirements for the siting, design, construction, operation, and closure of disposal facilities, criteria and requirements for the waste foam, packaging, any backfill and sealing material, and other components of the facility, and requirements for the involvement of the interested parties. The operator of a disposal facility for radioactive waste shall be responsible for its safety. It's common in most of the countries. The operator shall carry out safety assessment and develop and maintain a safety case, and shall carry out all necessary activities for site selection, evaluation, design, construction, operation, closure, and if necessary, surveillance after closure, in accordance with the national strategy, in compliance with the regulatory requirements, and within the legal and regulatory infrastructure. It's requirement 3 from Special Safety Requirement 5. So, and again, I'm not going to do it right now. If we will have time, I definitely will spend some time on safety assessment and safety case. But if you will click on this link from this slide, you will directly come to the slides focused on safety assessment and safety case. I'm not going to do it right now. The operator should supply all information relevant to the safety case and supporting safety assessment to the regulatory body, together with any other documents necessary to demonstrate safety, and through a process of iteration, demonstrate compliance with the regulatory requirements and with the technical specification of the facility. The operator should identify and seek to prevent potential conflicts between efforts to address long-term safety objectives and operational objectives. For example, operational expediency should not jeopardize long-term safety functions. Nor should site workers be subjected to undue risks in the interest of long-term safety. So it's not specific subject of this presentation, and in principle, this statement really covers this aspect. But previously, when we were talking about disposal, we mostly were focused on the post-closure phase of disposal facility. Just considering that during the operational phase, the safety might be easily managed by controlling of radiation exposure of workers and so on. But the fact is that it's not so easy. It's one point. Another one, that operational phase of disposal facility usually lasts at least a few decades, and during these decades, some accident might happen, some technical or technological changes might take place. So, and it means while it is much more relevant for deep geological disposal, but in principle, even for a near-surface disposal facility, quite often when we come to the point of closure of disposal facility, the real facility will differ from the one for which we obtain the license for construction and operation. So, and that's why it was found that even for a surface disposal facility, it's also equally important not just to control the safety during operational period, but also evaluate and assess safety for operation, and always, how to say, try to keep in mind the final stage. So if any changes applied during the operational period will keep the facility in the safe state for the final closure, or the changes we are implementing now maybe for the better purposes, maybe to provide better safety for the operational period, if it might jeopardize the safety for the long-term period. So it was found, how to say, last time, and I hope that it will be reflected during revision of this document in the nearest future. So, this is just to demonstrate, because we were talking about responsibilities of the operator. But in fact, as it was mentioned, three key players are involved in the disposal project, starting from the government, regulatory body, and operator. And this slide is just to demonstrate that the role of different stakeholders really change in time, starting from the point when the government indicated the need for action, need of creation of disposal facility, developing disposal concept, site selection, construction, operation, closure, passive institutional control, and post-licensing period for any surface disposal facility. The role of, how to say, and responsibility of three key stakeholders changes and evolves in time. So this document, SSG 29, has a special chapter on safety case and safety assessment, but as it was mentioned, it's a really very general, a very key point related to an surface disposal facility, because it is another safety guide focused on safety case and safety assessment for disposal of radioactive waste, which brings much more detail about the safety case and safety assessment itself, about its structure, what they should include, and how it should be performed. And again, now I'm not going to go deeper, but maybe I do hope that we'll spend some time on safety assessment and safety case for disposal facility after the end of this brief presentation. So the next chapter is also very important. It's about stepwise approach to development of surface disposal facility. And in this document, we do not use the term, but in practice and in not safety standards, but in informative publications, we use it more and more often. I'm talking about the term, the roadmap for disposal. So, and from this point of view, stepwise approach and the roadmap for disposal are very closely related. So to understand what steps we should implement really for realization of disposal project. And that's why maybe we'll stop a little bit more on this stepwise approach on development of an surface facility. And again, just to highlight that if you will click on the link of waste acceptance criteria, you will get just a few slides related specifically to waste acceptance criteria. And if you'll have time after the end of this brief presentation, we can easily jump to it if you're interested in this, for sure. So because I'm sorry, I do not see your faces, I do not know your background, how to say your duties, your interest. That's why this presentation is really like more informative, but with many options to focus on some specific topics if you will be interested in. So elements of a stepwise approach to development of a near surface disposal facility. So disposal facilities for radioactive waste shall be developed, operated, and closed in a series of steps. Each of these steps shall be supported as necessary by iterative evaluations of the site, of the options for design, construction, operation, and management, and of the performance and safety of the disposal system. And it is taken, this is a requirement taken from SSR 5. And just by the way, it's one more reason why I didn't focus specifically on these specific safety requirements, because the key requirements from here are repeated or quoted in this safety guide we are talking about right now. So if looking at the lifetime of disposal facility, we can identify at least a few main phases of development of the project. This so-called pre-construction activities, construction activities, then quite often it's going in parallel operation of already constructed elements and walls or cells, and in parallel constructions of additional walls. Sometimes even closure of already filled walls might go in parallel, and this might include 3 parallel processes simultaneously. So then it's a post-closure activities usually included active institutional control and passive institutional control. What is important that at least to jump from one stage to another, in most of the cases, a regulatory decision is to be made. And the basis for such a regulatory decision quite often is safety assessment and safety case. Moreover, I would say it even during pre-construction activities, even during design phase, safety assessment might be used as a very effective instrument to optimize a design decision. So to make a facility really safe, but from the other side, really effective from financial point of view. So, but in any case, in the national regulation and legislation, usually some points, at least moving from one stage to another, are indicated as a how to say time for licensing, for reconsidering license, and at this moment, performing safety assessment and developing of the safety case are needed. So key supporting programs, for example, site characterization, design activities, environmental monitoring, safety assessment, and record keeping should be ongoing over a number of steps in the development, operation, and closure of the disposal facility. The safety case should inform the site characterization and design programs of the relevance of uncertainties. So we do not have time during one presentation to go deep into safety assessment, because when we are talking about uncertainties, it's in most of the cases, it's really more related to safety assessments. I would say it's some kind of safety assessment term. At least the origin of it, it's much clearer and understandable when we discuss the safety assessment, but we do not have too much time for this. But in any case, I already mentioned that safety assessment might be used as a very effective and useful tool during design, but as it's written here, it's also not less effective, but might be even more effective even for site characterization, because when you try to perform safety assessment, you definitely need to understand what your site is. You need to know some characteristics of the site, and not only number of the layers and characteristics of the layers of the site going from the surface down, and characteristics of the aquifer and maybe temporary water bodies, underground water bodies, and so on. And to understand this, if you do not have exact site-specific information, which in fact you try to obtain during this assessment, during this, I would say, assessment exercise, you can identify which data are most critical in terms of safety. Just for example, if you know that some layer of your site is sand or loamy sand and it's well defined, you might do not need to spend additional efforts and resources to precisely define the filtration characteristics and porosity and some other specific features of this layer. If you exactly know what is it, loamy sand or something like this, because the impact of this, how to say, a difference in specific numbers will not affect too much, and the final dosage you will obtain when you perform the safety assessment. What is much more important for different layers of your site is sorption properties of the site for different radionuclides, and so on and so on. So when you try playing with the safety assessment, you will identify some priorities for the site characterization. When you already preselect the site, what features are most important for safety, and for which features you need to spend much more resources to get the site-specific parameters later to be used for safety assessment and demonstration of safety to the regulatory body when you will apply for the license. So that's why it's told that safety assessment and safety case are very important and should be implemented, in fact, at each stages, even if you do not need to get the license for site selection. In some countries, it's just informing a regulatory body that the site is selected, and all the features of the site are considered in the joint licensee for construction, for example, a facility, when design is already prepared, while in fact the design should be adjusted to the site properties. So even in this case, when formally the operator is not required to develop the safety case, it's important to develop it, to understand the system better, and to get how to say, the proper parameters to reduce the level of uncertainties, and how to say, to make data you obtain more reliable, so when you will apply for the license to the regulatory body. So the step-by-step process is an iterative process that should maximize the value of information as it evolves over the series of steps. Yes, again, so when coming back to this stepwise approach, so and initially when it is siting, you almost do not have information about design. So because just keep in mind that at the very first slides, when I started this presentation, I told you about disposal system, which in fact includes the site, the design of your facility that should be adjusted to the site characteristics, parameters of the waste. Also, so all organizational procedures, especially is more important for operational phase. How are you going to manage? How are you going to handle the waste during the operational period? And also the part of biosphere, so where the people is living, how radioactivity may be transferred to these people, how the dose for these people may be transferred. So all these aspects are equally important when you try to evaluate the safety of disposal facility, and when you try to find the appropriate site, try to optimize safe enough design and also optimize activity itself during operation of this disposal facility. So, but coming back to the site characterization. And the siting process for radioactive waste disposal facility, 4 stages should be recognized. It's a little bit, how to say, more detailed on the siting itself. The conceptual and planning stage, the area survey stage, the site investigation stage, and the stage of detailed site characterization leading to the site confirmation for construction and disposal facility. And the last, how to say, bullet related to detailed site characterization is especially important for adjusting the conceptual or initial design of disposal facility to specific site characteristics, really to construct disposal and reliable, safe and reliable disposal system. So, and the information concerning the first 3 stages is given in the appendix to Special Safety Guide at 29. So again, here you see just mentioned stages of siting in a more or less graphical form. So when they are really subdivided in area survey stage, when we usually are talking about screening from many to one or several sites, sometimes based on the archive information and former geological and hydrogeological investigations of the national level. When these several sites are, I'd say, pre-selected for the next investigation, this already site investigation stage is going on, and based on site-specific investigations, obtaining the properties of site-specific site, so selection of one or more preferred sites for detailed characterization usually is made. So quite often, so it's no need to report all the stages to regulatory body and to get the approval to move from one site inside to the stage to the next one. But as I told, if you will keep developing safety assessment and safety case, it will make your process more effective and will help you to prepare to this moment when you will need to submit safety assessment and safety case to the regulatory body on the next stage, for example, to obtaining the license for construction, or maybe even for construction and operation of a disposal facility. It depends from country to country, and it's, how to say, it's the not the ideal approach, but the reasonable approach that could be implemented. But the legislation aspects, the regulation aspects are definitely national dependent. So site characterization, the conceptual and planning stages of the siting process should take into consideration the fundamental limiting parameters for the disposal facility. The operator should address issues such as the type of waste, maybe not the waste class, but just the type that are supposed to be disposed here. The projected waste volume, because again, it will define how large site you are looking for. Basic requirement for the site in terms of nearest villages, rivers, main roads, and some other things, maybe even neighbor countries. Specific criteria that would disqualify a site from consideration, like recreation area, or really very close to the national border, or maybe any others, depending what is stated in your national regulation legislation, including the international agreements and conventions and so on. This information will help the operator develop a generic concept of the facility. Work completed at this step should serve as the foundation for the next step, the area survey stage. At this stage, the desirable features and possible limitations identified in the conceptual stage should be used to focus on one or more potential sites in the region of interest. The operator should narrow the region of interest by focusing on areas with appropriate features and characteristics that would accommodate the generic conceptual design for the facility. So, and on this stage, when we are talking about conceptual design, we usually look around the world, looking at neighbors countries. Neighbors countries are mostly in terms of they have very close type of climate, maybe close enough type of culture in terms of people, in terms of population, maybe even similar, not the same, but similar level of resource development and so on and so on. But in principle, of course, you can look around all the world, trying to identify the design that it is or planned to be used for similar type of radioactive waste, and consider this very general description as a conceptual design. So, and sometimes different conceptual design will cause different not requirements, but specific features for the site for this conceptual design. That's why it's not fixed, it's not required, but it is recommended on the very initial stage to consider several conceptual design and several potential sites, because one site might be applicable for one conceptual design, another one might be applicable for another type of conceptual design, and on the next stage, the decision how they might be made, which option to be selected, addressing both safety aspects and also infrastructural aspects and social aspects and many, many others. So after potential areas is selected, the next step is site characterization, when the site is already selected. And site characterization is an activity undertaken in order to understand the natural features, events, and processes at the site at the present time, in the past, and potentially in the future, and to describe their spatial and temporal extent and variability. So here, even the term features, events, and processes again more related to safety assessment. I'm not going to stop on this, but just keep in mind that again, it's one more link between some practical activity and safety assessment. Site characterization should contribute to a comprehensive description of the site that is sufficient to support development of the safety case and its supporting assessment. For an surface disposal facility, this description should include information concerning the surrounding population and land use. The context in which site characterization is carried out and a clear understanding of objectives should be set down to define properly the extent and focus on the site characterization activities that are to be undertaken. Again, it's a link between safety assessment, safety case, and activity related to implementation of disposal project. So next step is detailed investigation leading up to and including the site confirmation stage should be undertaken at the preferred site to characterize the host environment in sufficient detail, to support or confirm the role of the site and its environment in the adopted safety strategy, to support or confirm the selection of preferred site or sites, to provide additional site-specific information required for a detailed design of facility, and provide additional site-specific information for the safety assessment. So, and as it was written, Appendix 1 for these special safety guides gives some examples of siting of a near-surface disposal facility. And siting is a fundamentally important activity in the disposal of radioactive waste. And in the siting process for radioactive waste disposal facility, 4 stages may be recognized. In principle, we went through these stages before, and there is no need to stop on this. The only warning, unfortunately, quite often I faced with this situation when geologists or hydrogeologists used to say, so we found the best site, so the facility will be safe. I would like to remind you once and once again, never rely on only one of the elements of disposal system, because disposal system includes site properties, engineering barriers, waste characteristics, and how to say, part of biosphere which is included into this in the area where this disposal facility is located. And only as a system, as a one system, it can be considered, and decision if it is safe or not safe might be made. So not going in more detail on very specific siting aspects, just to inform you that Appendix 2 includes guidance and data needs for site investigation and site characterization. You see 3-4 slides. Coming back to the content of the safety guide, we have chapter 7 on assurance of safety, which includes monitoring, post-closure institutional control, accounting for nuclear material, security, and management system. And as it was already mentioned, some paragraphs related to existing disposal facilities. So again, just to remind you just to remind you what I already mentioned it, because even when we are talking about disposal facility, and when we try to address a lot of uncertainties related to variability of characteristics of environment, of the host rocks, of hydrogeological conditions, and so on, especially when we try to address uncertainties on the future behavior of each of the component of disposal system in the far, far futures for hundreds of years. But please think a little bit about the operation of a disposal facility. What is the difference between operating a disposal facility and storage facility? For sure, the difference is, but if it is really too much, so, and how to evaluate the safety of disposal facility during operational period. There is no any specific safety assessment methodology for disposal facility, not for post-closure. For post-closure it exists, but during operational period. So, and that's why for this operational time, quite often it's important not to forget about safety standards for pre-disposal, and in particular about safety guide on storage, and what is much more important, a safety case and safety assessment for pre-disposal management of radioactive waste. So if you will read this document, you will not find that the scope of this document really address operational period of disposal facility. But from the other side, we do not have other document specifically focused on such aspects like safety during operation of a disposal facility. And in practice, I know a few cases when even this document, and in particular safety assessment methodology for predisposal, was effectively implemented and used to address safety during operational period of disposal facility. So I'm going to an end. And just as a summary, to say that countries should identify and develop disposal routes and facilities for their radioactive waste. Do not delay, because development of disposal process is a very lengthy and very resource consuming process. And the earlier you will start at least thinking of it, the more chances you will succeed on this way. So disposal facilities must comply with the safety principles and the requirements for disposal. A safety case and disposal safety assessment shall be used to guide all decisions on waste management, including disposal. All work shall be done in accordance with the management system. In fact, that's all from the, how to say, key part of my presentation. But as I told you, how to say, during presentation itself, I have more slides if you will be interested. So specifically on safety assessment and safety case, a few more slides about waste acceptance criteria. So now I stop sharing and waiting for, I would say, your questions or indicating of your interest. What would you like me to tell about during the, how to say, remaining
Thank you. Thank you very much. Any questions? Not at the moment. I again have one. So several years ago, I don't really know if it's true or not, but I've heard that there was a discussion in some international forum, maybe at IAEA, about the let's say future language or sorry, had some problem with connection, yeah.
Yes.
Okay.
Just try to speak anything.
Okay.
It looks like now.
Is it okay now?
Yeah. Yes.
Okay. So a few years ago, if I heard, there was a discussion about the future language or future understanding of the modern science and languages by future generations, and it was discussed that near these repositories there should be some science or text that can be understandable by future generations. Do you know something about this? Because I never seen the materials of this discussion.
It's okay. From the very beginning, I was not directly involved into this discussion because it's a special, I would say, direction or part of the IE activity, like related to knowledge management. And there are specific publications on the knowledge management. I only know that it really were few debates. So what would be better for the future? Either to make some kind of pyramids with clear signs that might be interpreted independently from the language, that some danger is behind this place or something like this, or vice versa, keep just the flat area without even any sign that something might be below this place on Earth. So, and as far as I know, no one direction, no one solution has won. So because people continue discussing this, and again, because IA isn't looking for the truth but trying to find the consensus wasn't found. So now it's kept to the countries. So it's up to the country, because again, you see, they have absolutely different countries even in terms of dimensions. So they have some very highly populated area in Europe, small countries, very populated, and so on. And it's almost impossible to imagine that in far future it will be nobody here. But from the other side, we have such countries like the United States, like Russia, with almost or real deserts, when no one is for hundreds of kilometers is living around this area. So it really might be different. It depends on many, many aspects, and no general recommendations were found from the IEA in relation for the knowledge management. How the only point is the IEA really insists in that the knowledge should be kept. But how the site itself should be identified for the future generations, it's up to the country how to make a decision according to the situation, what's better. And again, not exactly to equation, but a little bit closer to it, and maybe more closer to the knowledge management. So how knowledge management was solved in Centre de la Manche in France, where they have how to say, big near surface disposal facility, which is now closed. So I would say that they have 3 level of documentation about the waste and facility. As soon as this facility is not completely delicensed, and it is still some kind of the monitoring phase after the closure, the complete and full set of the information is kept under this how to say operating facility. Some extraction with the key information from this how to say all set is kept in the municipality. And the most important information, it's a low information, is, I can't say printed, it's somehow written on pergament, not on paper, not on magnetic, I don't know, USB drives or hard drives or something like this, but it's really written in pergament that might be kept a few hundreds of years, and then kept in Paris, in the capital of the country. So it's about really knowledge management, to keep the knowledge. But if the site itself should be really clearly indicated, clearly for everybody who might come to the site later, there is no any general recommendation on behalf of the IAA, at least as far as I know.
Okay, thank you. Very interesting. Any other questions? Not at the moment, but we will share the presentations and your contacts, so everybody.
Yes, I'm open. Please, if you will later have questions related to my presentations or related to waste management, you are always welcome. Even in case if it will be related more to technology or some other aspect, not to the safety, I will try to contact you, how to say, with my colleagues from the waste technology section, and maybe they will, if they will have time, they will try to assist you. So just in a few minutes, I will send this presentation to you to make it available, and you are welcome to ask me questions. Thank you.
Thank you. Thank you very much again. So, and now we have one more short break, maybe 10 minutes at this time, and we will continue with the last presentation and with some dinner. Okay.
Okay. Where are all the people? Let's continue with our last for today lecture on the treatment of liquid and radioactive waste. And let's start with the pre-treatment of the waste. So you've heard about the safety standards for pre-treatment of radioactive waste from the lectures of Michael Ojovan. So the pre-treatment mainly consists of several operations. It's collection, segregation, decontamination, adjustment. That means that mainly chemical properties adjustment, and fragmentation. So the collection means that we make processes to collect and to transport to the further pre-treatment operations all the radioactive waste that are generated in our facilities, in NPPs or other facilities, medical facilities, whatever. After collection, we segregate materials. So that means that first of all, we split our waste onto materials that are not really contaminated, so the activity is below the exemption limits. And second stream of this waste is really contaminated materials. So already on the stage of the pre-treatment, we can reduce the volume of the radioactive waste simply by splitting or segregation of these two types of materials. And then the separation of the radioactive materials can help further to make it easier to handle different waste. For example, we can put combustible waste in one way, non-combustible to another stream, and it will make further processing of this waste much easier. And the splitting of the waste on non-radioactive and radioactive further can be used also, or it can be a step before the recovering of some non-radioactive materials that can be reused or that can be recycled. So decontamination, normally it works with the metal materials and metallic materials and some concrete or cement materials. The main purpose of the decontamination, again, to reduce the volume of the radioactive waste, because if you just remove the thin layer on the surface of the metal that is contaminated, you can significantly reduce the total volume of this type of waste. Adjustment, that means that sometimes mainly it works for liquid radioactive waste. The chemical properties of these aqueous solutions can be difficult for further treatment. For example, it can be very acidic or very alkaline pH that is not suitable for the existing reprocessing technologies. So one of the stages of the pre-treatment is adjusting the pH, the salinity, the presence of the organic components, or to remove some solid particles in the solutions. So it is adjustment of these solutions for further treatment. And fragmentation, again, it is mainly for or it is for solid waste. Again, it makes the solid waste easier for further treatment, because either you have the whole wall of the building, or you have some small pieces of the concrete that you can further treat with some processes. So the treatment itself, the main objective of the radioactive waste treatment, of course, it is reduction of the volume of these radioactive materials, because the lower, the smaller the volume, the less money you will spend on the disposal of this waste. It is a removal of radionuclides from the waste and concentrating them in one stream. So again, you from this removal, you decrease the total volume of the contaminated materials. And again, change of physical and chemical compositions to make to make these materials more safe for further storage or disposal. So change of physical and chemical properties means, for example, liquid waste, that you make the liquid waste solid. You immobilize these liquid components in the matrix, or you destroy some organic components that can be flammable or that can be used by, I don't know, bacteria, for example, for their living. So you change the chemical composition to make your waste more safe for further storage. And treatment, the way how you select the treatment of certain waste stream depends on these many requirements. Of course, I would say the main requirement is the properties of the waste that you will work with. Then there are clearance levels, so what you can do to make to decrease the volume of radioactive materials as much as possible. So it depends on the clearance or on exemption levels in your country. Then it is requirements for conditioned waste and for processing of secondary waste. Don't forget about the secondary waste. Every time, again, when you work with the radioactive material, even if you treat the radioactive waste, you will generate the secondary waste. Every time you work with radioactive materials, you generate waste. The volume of secondary waste, of course, should be lower than the volume of the radioactive waste that you are working with, but still, it is you cannot avoid the formation of secondary waste. So even if we will talk mainly about the liquid and solid radioactive waste, there is just one slide about the treatment of gaseous or airborne waste. There are just few methods to work with them. It is filtration, it is sorption, it is cryogenic trapping for some inert gases. It is delay or decay, and wet scrubbing. So the filtration means that we use efficient filters like HEPA filters that have very small diameters of pores. And these HEPA filters allow us to catch a lot of particles, a lot of aerosols on these filters, and thus we decrease the radioactivity of gases by catching the radioactive aerosols. Not really the gaseous products, but the aerosols in these gas streams. And as a secondary waste, of course, we will have these HEPA filters and some pre-filters materials. Sorption for some active species like iodine species that are produced during the reprocessing of spent nuclear fuel or some other elements like technetium, very volatile material, or some other. So if we have some active gaseous species, we can use some specific sorbent materials to catch these elements. For example, for removing iodine, you can use charcoal or zeolites where some silver incorporated, just a very thin layer of silver, and iodine will be efficiently captured by these filter materials. But it will work only if you have let's say elemental iodine. if you have organic iodine, so like methyl iodide or something like this, these filters will not work. So you will need to have some additional pre-filtering system where your organic iodine can be damaged or decomposed to the iodine and some organic volatile materials. And then after this pre-filtering system, you can catch efficiently iodine. Is one of the options. And again, as a secondary waste, we produce these spent sorption materials. Cryogenic trapping works with the inert gases that cannot be caged by other methods. So you just use the trap with that is cooled either by liquid nitrogen or liquid helium, or depends on what you are catching, depending on the temperature of the melting of your material. And then you store it for some time. You put it further in gas balloons and store it for a certain period of time. Sometimes you don't need to catch the material for short-lived gaseous product. You can just make a system with the long pathway where your gas will go for a very long time, and during this period of time it will naturally decay to the stable nuclides, to the stable elements. And wet scrubbing also is to catch some chemically active species where you just bubble your gases through a vessel with some specific liquid. Depends again on the chemical properties of your elements. So aqueous waste. For aqueous waste and for solid waste, you'll see this type of diagram. The main questions here is the waste suitable for clearance? If yes, you just discharge it to the environment or to the some specific, not specific, just some industrial, let's say, storage. If not, then there is a treatment procedures where you again produce secondary waste, you have some concentrates, and you have a stream that can be discharged to the environment. So there is a separating of your component of the waste streams by the small volume of the concentrate that you have all or most of your radionuclide. And a large part, it is good if it is large part, of the non-radioactive, let's say, or very low radioactive stream that you can discharge in the environment or recycle. So there is a general scheme. You have this aqueous radioactive waste, and after the treatment, you have the water that you can discharge and a sludge or some concentrated material, sorption material, sorbent materials that you should further dispose. And to evaluate the efficiency of the treatment of the liquid radioactive waste, you can use this decontamination factor that is actually a ratio between the initial activity of your liquid waste and the final or purified final activity of your purified solution. Pre-treatment of the liquid waste is important because if you use pumps, if you use membranes, filters, and you don't adjust the chemical composition of your liquid waste, then you can have a problem, just a technical problem with your equipment. So just like clogging pumps or damaging of the pumps. So the pretreatment of the liquid radioactive waste is important, not only from the point of view of the chemical process, but simply from the point of view of the technological performance of your processes. Sometimes the chemical adjustment needs to add some oxidizing agents or flocculating agents to remove complexing agents that can decrease the efficiency of your absorption, for example, process or filtration process. So again, the chemical adjustment and some prefiltration of your liquid waste, it is really important for further treatment. And nowadays, these four methods, chemical precipitation, ion exchange or absorption, evaporation, and a few membrane methods, they are most developed and the most used methods for the treatment of radioactive waste. But they're used not alone. Very often you can see these technological schemes. There you have sedimentation, filtration, and some other processes together in one technological scheme. Let's go briefly through these three basic methods. So chemical precipitation, ion exchange or sorption, and evaporation. So evaporation, of course, I would say it is one of the most expensive methods because you need to heat your volume, big volumes to high temperature, to 100 or sometimes a bit more Celsius degrees, and wait when all this volume will, or not all, but the most of this volume will be evaporated. So it is a very expensive but very efficient method because you can decrease the volume quite efficiently. Normally, it doesn't depend on the chemical composition of the solution. It only depends on the concentration of salt. So because you cannot avoid just the formation of the salt after evaporation. And if you have, but evaporation very often used for solutions with high salt content, because in this case, you cannot really use, for example, ion exchange. It will not work because all the capacity of the ion exchange resin will be so saturated, and there will be no chemical exchange. Thus, the evaporation can work with these very saline solutions to remove water and to compact these materials. And very often in nuclear power plants, for example, they use it to produce this concentrated salt. It's not really a solid salt. It's like a paste, let's say, of this very concentrated salt suspensions, I would say, or sludges, and evaporation cannot be affected by the chemical composition of your solution. Only problem may be if you use some products containing ammonia and nitrates. In this case, you can produce an explosive like ammonium nitrate, and if you evaporate it, there can be a problem. So there is only, I would say, a case when you not you can use evaporation, but if you destroy these ammonium containing solutions, you can use some formalin for destruction of the ammonia or some other chemicals. So evaporation is very efficient, but quite expensive. Chemical precipitation, as we've seen from the presentation of Natalia Kuzmenkova and from my presentation, is very also very efficient methods to concentrate radionuclides. You can select the specific carrier to remove the radionuclides that you would like to remove. So it's a relatively low cost of this procedure, and you can use it in many applications. There is almost no negative effect, only maybe if you have some either complexing agent or some oils or some other organic impurities in your aqueous solution, then it can be some not very good efficiency of your process, but you can avoid this by pre-oxidizing of these components to remove them, and then your precipitation or co-precipitation will work very efficient. Ion exchange works very well, so it's very good method to remove radionuclides, but only if you have low salt content in your system. Again, if you have very high salinity, then your ion exchanger will be saturated, and there will be no further chemical exchange. But ion exchange can work very good for very large volumes. For example, one of the application of this method was during the purification of the small lake in Chelyabinsk region near the Mayak facility. So just imagine that you pump the volume of the water that is the whole lake, even if it is small, but still it's a large volume of the liquid waste. Of course, as far as it is natural lake, the amount of the salinity is very low. So in this case, you can really use this ion exchange technique to remove the radionuclide from these huge volumes of the solution. So it's very efficient, but you can choose among this method depending on what exactly the composition of your solution, what is the volume of your solution, and what the decontamination factor you would like to reach. Membrane technologies, we can classify them with the size of the particles that are filtrating through the different pore sizes. So it's either microfiltration, so it's the biggest particles that are filtrated. Then it is ultrafiltration, so it's smaller particles. We can call them colloidal particles. And then nanofiltration, that is very close already to the osmosis. So we separate very small, maybe polynuclear species from the real solution. So it is the most, let's say, most efficient step of purification, but you cannot use it directly without filtration, microfiltration, and so forth. Because otherwise, again, you will clog your filters, and it will be not possible to press your solution through the filter. Of course, in all of these methods, we produce a secondary waste that are membranes itself. But again, this technology, they are very efficient to remove very small particles. If you have not a pure solution with your radionuclide, but sometimes it is especially important for polyvalent cations like actinides or, I don't know, zirconium or other polyvalent cations that can absorb, that cannot produce, that can produce their own small precipitates, but also they can efficiently be sorbed on the surface of the small particles, of the colloidal particles. And to remove these polyvalent cations that are sorbed on colloidal particles, you can use this microfiltration and ultrafiltration techniques. And to obtain the pure solution without any radionuclide content in it, we can use osmosis. The decontamination factor depends on the concentration of the radionuclides in initial solution, but, and again, as usual, we produce the secondary waste that are used membranes. These main methods for treatment of radioactive waste. In every of this treatment, we produce the solid radioactive secondary waste. It is either sorbent materials or membranes. And then we should treat this solid waste, not only this, of course, but the secondary waste from the liquid waste treatment. They are included in this scheme. So again, the main objectives of any treatment, including the treatment of solid waste, it is the volume reduction, removal of radionuclides, and again, change of physical and chemical properties. And again, here we have this chart where the first question, is it possible to discharge the materials? And if yes, then if the activity of these solid materials below the clearance level, we just put it in as a industrial waste and remove it, or we recycle it and use it again. If not, then we can store them for some certain period of time for decay of the radionuclide inside this waste, and then put again as an industrial waste or to recycle this material. But if the activity of these materials is very high, so it's not suitable for clearance, then we segregate this material, so this pre-treatment of the solid waste. We separate these materials on two waste that can be treated. So treatable materials and untreatable materials. So untreatable materials goes directly to packaging and for further storage and disposal. And treatable materials, they goes to the pre-treatment where they can be decontaminated, and part of the waste can go again for the exemption, and part of these materials goes further to the segregation by other characteristics, for example, non-combustible and combustible materials, and so further treatment of these two types of materials with the final aim to package these materials in the form of matrix, of some matrix, and then transport to the storage facility. So, and one of the easiest way to treat the solid waste, it is of course compaction. So just pressing of your materials if it is possible, and it is either low force compaction, so it is not very huge forces that are used, or super compactors that can be used if it is possible to reduce the volume significantly. In this case, use very powerful presses. So, and compaction can be done immediately in the containers. For example, one of the facility of the Russian enterprise that works with the radioactive waste, they have this compacted system that allows the compaction of the materials directly in the container. This part of this press machine can be left in the container if it is very contaminated. So it is a removable part, this part, and very efficient to to compact the waste directly in the container. So you don't produce actually any secondary radioactive waste in this case. Also, it's not high forces, not high compacting forces, but the compaction takes very few time, so very fast process. These many compactors they have additional system for purification of the gaseous streams, and in this case we produce secondary waste that are HEPA filters of this gaseous stream. Thermal treatment. There are several approaches: direct incineration, pyrolysis, plasma, and metal melting. So metal melting, from the name of this method, means that it is suitable for metal, metallic compounds. Incineration is technology that is used for a very long time, and it can work for both solid and liquid waste. Pyrolysis, it is, I would say, developed industrial method, but for radioactive waste, it is not so widely used because of the formation of the volatile organic species that cannot be completely absorbed by this off-gas purification system. So we tried it for different liquid waste and for solid waste like resins mainly. So it's organic waste, but the problem, not from the technological point of view actually, but from the regulatory point of view, it is formation of these volatile of these gases that are really flammable. So it is good for industrial application. Then you put some organic material and you produce the flammable gases, because you can use them to make electricity, to make heat production. But for radioactive industry, it is not very good. So it depends on the conversion rate of these organic components, and not often used in radioactive technologies. But plasma, it is interesting method. It has higher temperature than incineration. For example, incineration, it is mainly up to, let's say, 1000 Celsius degrees, and plasma has a temperature above 1500 Celsius degrees. So it's a higher temperature, and it works very good both for solid, liquids, metals, whatever. Just put it in plasma and you will produce a sludge. So it's again one of the examples from our good partner from the Radon enterprise, and there is example of this incineration furnace, and temperature here, yeah, you can see it's 900 plus minus 50 Celsius degrees, and it works both for solid and liquid radioactive waste. And volume reduction factor is not very high, but it's also okay. But so it's another example of the incineration plant. In these plants, you will see it also for plasma plant. You will see very often this very complex system of the purification of the gas streams of this off-gas cleaning system. But again, for incineration, there is still a need of the separation of the combustible and not combustible components of the solid radioactive waste. And plasma, again, plasma has very high temperatures. You can see it here. It's on the right. It is 1585 Celsius degrees. So it's modeling of the distribution of temperature inside this shaft. And you put your materials from the top of this shaft, and at the very bottom, where the highest temperature is, you produce a sludge, or it can damage organic components. For example, you have here the same pyro gas, so it's not oxidized organic gaseous product that can be again further used actually for production of the electricity, for example. But anyway, so here you have very high temperature and you melt everything. So you can put there any solid, metal, whatever, you will produce a sludge. So it will be a melt that after cooling looks like a glass-like slag. And you can use these high temperatures for almost any kind of the radioactive waste, even for non-combustible waste, because you don't need for this waste to be burnt. It's just melting of these materials. So this is how it looks like. So very high temperatures, and this is a container with this slag that is cooling down step by step. And if we compare these two thermal methods, first of all, again, the plasma methods can be used for non-combustible components, and incineration is not suitable for this kind of the materials. And as a product, in the plasma method, you produce this melted glass-like slag, very compact materials with high mechanical strength and chemical durability. In the case of incineration, you produce ash, so it's just a powder of the burnt materials, and this ash material will require further additional processing to be immobilized in cement or other matrices. Yeah, so actually, plasma method is very good, but of course more let's say sophisticated, technically sophisticated, and maybe more expensive. Here is an example of this coefficient. It is the volume reduction factor, and you can see that if you have no, it's strange. So actually the more components it's non-combustible. I thought it's combustible. Yeah, if you have a lot of combustible components, yeah, here for example, you will reduce the volume very efficient, yeah, because they will be evaporated. They will produce this pyro gas, the off gas, and the maximum reduction of the volume can be very high. In incineration furnace, you remember it was something like around 4, yeah, and here it is around 40. So it's much more reduction in the volume, and you put your slag directly to the container, and then you just collect your containers in other super containers or overpacking, and then it is the final form for your storage, for example. So the plasma is very good, but again, it is sophisticated method. And also there is an example, this Pluton plant. It is again located in Radon enterprise, and they analyze these off gases of their plant. And you can see that by the concentration of the different hazardous components like organic components, toxic organic components, or heavy metal concentration in off gases, they are low enough to be suitable even to European standards that are very high. And again, there is an example of this, of one of the plasma plant at Novovoronezh NPP that was commissioned in 2017, so 7 years ago. And this is an example of the resulting slag that again directly located in the container, and then these small containers are packed in the bigger one. And as I mentioned before, all this either incineration or plasma, all these thermal methods, they require a very efficient system for the purification of gases. And this is an example of how it looks like. After the treatment, either of liquid or solid waste, we condition this waste. We put it in some specific waste form materials that we already discussed last week, and this is some requirements. I will not go in detail through this. And the final step for these materials is the disposal in the specific facility. And there is three main components of this system. It's the site itself, it's a repository, this construction, and the waste package. So, but you've heard this nice presentation from the Andrei Guskov in the previous lectures. So, and yeah. So what is today very needed, or I would say that it is the main areas where a lot of research work is currently undergoing. So of course it is the less use of the human resources. You should avoid the participation of the people in the process if it is possible. And to do this, you can use online control of all the processes, different techniques to do this. It is automatization as many processes as possible, or even robotization. So it's a bit different definitions, but still you can imagine that it is less use of the human forces. And that is very important for analytical operation. It is miniaturization of these analytical techniques, because if you don't take into account the radioactive waste that are produced in analytical lab, it can be possible that you will produce maybe not the same amount of the secondary radioactive waste, but significant amount of the radioactive waste that goes off your analytical lab. Very often people don't consider this waste at all, but it's really a huge amount of the waste that goes from the analytical laboratories at these facilities. So yeah, this is necessary to minimize the presence of people. And when we're talking about the different processes, either in treatment of radioactive waste or fractionation of the spent nuclear fuel, so what are the requirements for the recovery or purity of different fractions of different materials? Of course, it is always a balance between the price and suitability, and how this can be connected to radio ecology, or let's say to the safety of the population in the country. I will just some general pictures that I hope will bring some ideas to you. So this picture you've already seen. we need to fractionate these highly active materials to decrease the toxicity, to decrease the hazard. But due to the thermodynamics, it is not possible to remove completely 100% all of your radionuclides from the material. So just law of the of the nature of the thermodynamics. Yeah. So some part of the radionuclides will still be present in your materials. Yeah. But at which level these long-lived radionuclides can be present in your material. To answer this, we should look on the concept of your repository or your disposal facility or disposal system, as we heard. Yeah. If you know this all this engineered barrier system, its properties, the properties of your natural barriers, then you can imagine what will happen if the worst scenario will occur. So the worst scenario, it is intrusion of the water in your facility and releasing of the radionuclides from your radioactive waste matrix, package, and repository. And when radionuclides go to the environment, there are a huge number of the processes that occur with your radionuclide. It is basic chemical process like precipitation, hydrolysis, sorption on different mineral surfaces, redox reactions. It is interaction with the bacteria. So many processes that must be considered to be able to predict the migration of the radionuclide. So if you know where is your repository is located, so you know the properties of your geologic media, so you have all these maps with the underground water flows, with the cracks in your geological media, so you know everything about it, you know the properties of your system. If you don't know, you investigate the properties of your mineral systems, your properties of your radionuclide in the lab, and you make a lot of natural investigation of how the radionuclide is migrating in real conditions, so you can verify your model that you obtain in the lab. And after this verification, you can build the model that can predict the migration of the radionuclide. But what does it gives us? From this modeling, it is possible to estimate not only the concentration of the radionuclide in the environment at some certain points, but that is important for us. It allows us to calculate the dose for the people or for the biosphere after a certain period of time. So you start with the composition of your radioactive waste. You put in your model the properties of your system, and after this, you can predict what will be the dose. And you know that there is a certain requirements for the maximum dose of that can be absorbed by the population. So, for example, it's just an example. It's not some certain numbers. I just took this common number. So let's say that after 1,000 years, if there will be the worst scenario in your system, the dose for the population should be less than 1 millisievert per year. So with all the properties, with all these chemical interactions and transport of the radionuclides, you put the requirements on the composition of your radioactive waste inside this certain repository. But you can reach this amount of the radionuclide in your radioactive waste. For example, it should be less than 0.01% of actinides. Yeah. So from this number, from these properties, it should be like this. So with these requirements, then you put requirements for the technology of the fractionation or for the treatment of the radioactive waste, how pure or should be your fractions, or what should be the maximum concentration of the radionuclides in your radioactive waste. And if you know these requirements, so it should be not higher than this amount of actinides, it should be not more than, let's say, 10% of cesium in your fraction. Then after putting these requirements, you finally made the requirements for your chemical system that you discover in the lab. So in this way, you have this relationship between the very long-term safety assessment, let's say, and the properties of the chemical system that you discover in the lab. So I think it is my last slide. Yes, thank you for your attention. As usual, if you have any questions, yeah, just take the mic. So the first person.
Thank you for your interesting presentation. I want to asking about the gas treatment, the waste. In the beginning of your presentation, you have explanation about the charcoal.
Yes.
Charcoal with charcoal. How to running this method? What can we have stream the gas and the gas passing the charcoal, or what process? And then the span of charcoal after after treatment. What can say this charcoal, this span charcoal as secondary waste? Thank you.
So for these cartridges where you put charcoal, you use special material. So it is charcoal, but it is produced in the shapes of a sphere with some certain size that you don't put very dense material in your system, otherwise the gas cannot go through it. So it's some specific size of the spheres. It is very dense materials, very mechanically strong, and you have these cartridges. So there is a normal flow of gas through these cartridges. And as a secondary waste, yeah, you have to deal with this charcoal. There are several approaches to deal with it. It is either put this material in polymer matrix like epoxy resin or something like this, or to put in cement, or to put in this magnesium potassium phosphate compound. So three main approaches to deal with it. Yeah. So
just a short question about the membranes. Can they also absorb or keep in any way the salts?
The salts.
Yeah.
So to do this, you can do it with osmosis. Yes,
Okay.
yes.
Osmosis, but not the membranes that we see.
Not
that
membranes.
ultra and
Not
nano and
membranes. Yeah. So, any other questions? If not, then I think our colleagues are on hurry already. So let's finish our Monday, our first day of the second week, and let's relax a bit during the dinner. Okay.